Good morning. After that marvelous night we had yesterday, we are going to continue our talks. And to begin with, we have the honor, the pleasure to introduce Professor Shinezana Histrova. And the title of his talk is Switching Signals in Dynamical Systems, Statement of the Problems, Construction of Solutions, Some Properties and Applications to Biology. Professor.
Oh, and I should say, of course, that we know each other since 1992 at a conference in Plovdiv with her advisor, famous Professor Bainov.
Former.
Maybe the young people don't remember, but yeah, he made conferences very lot of conferences every year even, yeah. So, and they were good conferences. Even I once met my future chair there. I didn't know anything about him or about Rolla or any. I asked where he's from. He said, Rolla. I said, where's that? He drew a map. And many, many years later, I was hired there. Yes. Okay, and then of course we have papers together and meet various places all over the world.
With many beer. Excuse me that I'm interrupting you. Okay, yeah. So, thank you to the organizers for inviting me here, for letting me to be the first time in Brazil. Now, first of all, I want to congratulate Martin. Who is Martin, of course? We know. But I would like to mention about these 60 years. 60 years of life. On one side, it's a lot. On the other, it's a little. But I would like, from my heart, to wish you to continue at least 60 years more with the wine, with the beer, and of course with mathematics in your heart. Yes, and not only in mind, in heart. Now, switch systems. What does it mean? I'll present the ideas of I could say, comparatively new actually study. Switch systems. What does it mean? It means that the finite family of subsystems, they could be continuous, they could be discrete, they could be any, I could say. And the switching signal that determine the initial, at initially given times, usually, at initially given times, how the system will be switched from one to another. How the right side part of the equations, roughly speaking, could be switched from one to another, from the given family of subsystems. This is the main idea of the switch systems. There are many real problems in which this actually characteristic switching behavior is actually there are some applications, there are some real situations in which switching of the behavior is can be observed. Okay. That's why now I'll present first with ODs, because this is very easy to be understood about ODs and the idea about ODs. What does it mean? A natural number, of course, is given, then the index set is given, and the family of functions. Finite set of functions. So, the switching rule could be different, but the most popular in the literature is about the piecewise constant function, which values are from the index set M. So, if the switching rule is equal to its value, one value, it means, for example, k from n, then we'll choose a function f sub k from the given family of functions. With other words, this is the definition actually of the switching rule. I would like to mention, to repeat again, that these points tau sub k, capital tau sub k, they are initially given in my first presentation in this one. So, for example, if we have just two functions, because it's the easiest case, one is not applicable, but if we, because if there is one, what will be switched? Immediately, no way. That's why if there are two functions, and the switching rule which could have values 0 and 1, no other values, because there are only two functions from the family, and we consider the scalar equation OD, of course, initial value problem. It doesn't matter. So this sigma could be 0. If it's 0, then we took f sub 0. If sigma is 1, we took f sub 1. This is the main idea of the switching. Very easy basic. That's why I'm explaining it on all this, to be able for you to understand. Okay, now, what will be the solution? Look, this is actually, the times, initially given times are 1, 2, 3, for example, just 3 points. Then from 0 to 1, we'll take f sub 0. From 1 to 2, we'll take f sub 1. From 1 to 2, we'll take f sub 0 again because of the switching rule, and blah, 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 and blah, blah, blah. So if we solve this very easy example and graph the solution, these are the solution. I would like to mention that in some sense, these equations are similar to impulsive differential equations. But there is a huge difference, because in impulsive equations, there is a jump at the point of impulses. Now, look at the graphs. The solutions are continuous at switching times, no jumps. It changes significantly the behavior and the study of this equation comparatively with impulsive differential equations. Okay, now, I would like just to mention that if we change the switching rule, of course, again 0 and 1, but look at another rules for changing the switching rule. Actually, then of course the system will be changed, and of course, if we compare all graphs, just graphs, nothing else, it's enough for you to understand. You can see that they are absolutely different because of the changing rule. Yeah. Okay. If we choose a rule, switching rule, which is just 1, then it will be activated just at one point, and there will be just one change of the system. There are some examples, of course, in which the switching rule will be not activated at all. That's why it's when we consider the system, switch system, it's very important to use a special switching crew which could be activated at least once, and to take care of the other very complicated situation when the switching crew is activated in finite number, and when the switching crew is activated at times which limit is not infinity, but a point less than infinity. These are very complicated cases, and we have to take care of it. These are typical actual phenomenon for switch system. Now, because of the title of the workshop, I decided to present one model on which we work. I'm not saying I work because I'm not working alone, I'm working with other people. I could mention who is my main co-author. Unfortunately, one of my main co-authors is not alive, Professor Agarwal. I'm so sorry about it, but it's the life. Another main co-author of me is Donald O'Regan. Fortunately, he's alive and very hardworking, extremely hardworking, I could say. Okay, and of course, Martin, who is in front of us. And now, consider a special network model. What kind of model? Look at number 2. The main actually characteristic of this model is so-called activated function. Function of activation, this H. Usually, it's in the Hill form. Look at this form. There is a constant A, and there is a constant B. Both constant could be changed. And if they change because of the model, because of the behavior of network, then of course the right side part of both equations, mainly of the first equation, into will be changed. When at some points, changing at some points means that there is a switching rule, and this switching rule, if it's activated, then this H will be changed. It's well known that this model too is not applicable only in biology. For different kinds of networks, in engineering, for example, it could be applied, especially in engineering, electrical circuits. We can use to switch from one to another, actually activation function. It could be it could be artificially, but it is. Now, if we choose the switching rule to be a constant on intervals, initially given points, switching points, and a switching rule which is equal to a constant or constants on this interval between two switching points, then we will have number 3, which is actually a system, I'm not saying model, okay, system, in which the right side part is different. Sometimes, if we consider, I'll go to the previous slide. if we consider this, for example, activated per function or functional applications, then in some cases this this alpha or beta could be 2 beta, usually it's 2 in the literature, but sometimes it could be 3, it could be 4. The same is about this A. Let's say A alpha doesn't matter. So, in other words, this right side part will be changed at some points. And there are 2 basic questions about the model. First question is about the equilibrium. What does it mean, an equilibrium point for this system? Yeah. First, we define an equilibrium on each interval. On each interval, if there is a constant which is satisfying this equality, then there will be an equilibrium, but on the interval between 2 consecutive, actually, 2 consecutive switching times. If we go further to the next interval, between the next switching times, then this equation will be changed because of this function h, and there could be eventually another constant, which is an equilibrium. So, what does it mean, an equilibrium of the system, the whole system? We define the global equilibrium, we call it the global, by this way. On the first interval, it's the first equilibrium. On the second, with other words, the equilibrium is again piecewise constant function which is changing at switching times. Very rare, I could say, that they are the same. Usually, these constants, these equilibriums from 2 different intervals are different. In very, very rare cases. So, now, what does it mean, exponential of stability? What does it mean, exponential stability? How we can define, for example, why exponential stability? Okay, because I decided to use it to present just this stability. There are similar definitions about other types of stability. But what does it mean, exponential stability for the switched system? It means that if we take a solution of the switched model, it consists of 2 functions, of course, because there are 2 equations. And we take an equilibrium of global, with other words, global equilibrium of the system, then the difference between both is exponentially close. Exponentially close because of e to a negative power. Nothing new under the sun. The new here is the definition of the equilibrium, I could say. And I'm presenting just the statement of a theorem, the conditions, just to see the conditions, they are not so strong conditions. Lipschitz for the activation functions, these inequalities because of the, we need for the proof of the exponential stability, and the claim. The global equilibrium is exponentially stable. Now, an application. If we take this, actually I took this from a book, biological book, which Donald Oregon sent me. It's a PDF, of course, and to choose some actual examples. And we discussed and decided that this is a good example. And you can see actually some graphs here. First, the graphs are in the case which is without switching rules, which was given in the book, of course, because up to now, most of the studied models are without switching rules. Now, let's consider a switching rule and a switching, an activation to activation functions, h sub 0. It's h sub 1 and 3. There is a typo on the slide, excuse me. H sub 0, h sub 1, h sub 2, h sub 2. 3 different activation functions, and of course a switching rule, and in spite of the switching rule, look, the solution is exponentially stable. But because of the appropriately chosen switching rule. We found some switching rules. I don't have time now to present this situation, but we found some switching rules in which the solution is not at the equilibrium global, is not exponentially stable. Because some of the previous, look at this, some of these conditions are not satisfied. About function h, no problem, it's illusion. But about this we want this. There is a problem. If there, at least one is not satisfied. So, we studied the case of finite sequence of switching time. There are some graphs. Also, we studied the case of infinite number of the switching time on this example, to show that in some sense it works, in some doesn't work, so on. Now, this is absolutely new. What does it mean, absolutely new? When you read the title of the slide, you will understand what is the main difference between this one and the previous ones. So, usually, it was actually provoked by real applications. And particularly, we found a paper in biology about sea snails, 2 types of sea snails, which behavior is described as a neural network. Okay, great. But we, at random times, there could be a change in these sea snails at random times. Between these 2 random times, the behavior is determined. OD. But at random time, change. It means that we have to consider switching or switched system of ODs, but in this system, the switching times are random. The presence of random times at the system led to change the behavior of the solution. Now the solution is a stochastic process. And it depends significantly on the type of the randomness of the switch rules. If they are, we didn't study everything. We studied just exponential distribution. Why exponential distribution? Because between two consecutive switching times, the waiting time is also exponentially distributed. And because of the PDF of exponential distribution, it's always exponential function. Great. Integrals are easy to be obtained. But we have plans to go for the gamma distribution, which is a generalization of exponential, of course. But it will take more, actually it causes many difficulties because gamma distribution is more complicated. Now, let's talk about the future. Now, again, what is the description of the model first, of the system, switched system? Again, we have a set of finite numbers and a family of functions. The number of the functions are equal to the number of this M index set, and a switched system. First, we consider probability space, and as I mentioned, actually exponentially distributed random variables independent. Definitely they have to independent because we need to find expected values of multiplied functions of random variables, so we need to be independent. Independent exponentially distributed random values, sequence which is a sequence of random variables increasing, let's say, because of the definition it's a sum of the random variables up to k, and consider switching rule, which, remember that this psi is a random variable. So, sigma switching rule will be equal to a constant, but for which values? Values between two random variables. Stochastic process. Not a function, regular function. Stochastic process. Great. And what is the meaning of the first given sequence of random variables? Actually, this is the time between two consecutive changing or activation of the switching rule. What is the meaning of psi? Psi is giving is a random variable, which is giving actually the time, more exactly the number of the activated random variables up to k. And number 5 is the definition of the system or scalar equation. It doesn't matter. It depends on f. If you look at it on the first view, nothing new. But remember about psi. Psi are not points on the real line, they are random variables. So this is not an OD, regular OD. This is an OD which has changed right side parts at random times. And it means that the solution of number 5 on equivalent number 6 is not a regular function. It's a stochastic process. Then, what will be the equivalence of the definition of first equilibrium, and eventually, and second exponential stability? Now, first I would like to explain how this system, the piece number 5, could be solved practically. Could, of course. Now, take values first. If we take, okay, it's better to go on this side. Think that initially we have these random variables down. They are the waiting time between two consecutive changing times. Consider some values of these random variables. Any type of values, but fixed. Then we could find the value of psi, which is an increasing sequence of real points, of real numbers. And then, if we go further to number 5 and replace this psi by their values, particular values, we'll have an OD, switched OD. And if we solve this equation, we'll have a solution, a real solution. This solution is called the sample path of the switched system. If we consider all possible sample paths, they will actually determine a stochastic process, and this stochastic process will be a solution of the switched system. And about the definition, number 3, about the exponential stability. Actually, because we have stochastic process as a solution, we have to consider expected value. And because it's very difficult, and now we do not know how to proceed in the case when the system 5 has no zero solution. We do not know how to proceed yet. But assume that it has zero solution, which means zero equilibrium. Then the solution will be exponential stable, but peak moment exponential stable, similar to the case of, similar to the probability theory, roughly speaking, if the expected value 8 power p is less than the exponential function. This is similar, again I would say, this is similar to the stochastic equations, this is similar to probability theory, and so on. But now, in this case, we are combining ODs plus some random variables to obtain something different than stochastic equations. I would like just to show a theorem because the conditions are not so strong about random variables independence. Of course, assuming that the OD, corresponding OD without any randomness in it, it has a solution. There are many results about ODs, about existence, about uniqueness of solutions, so many equations, global solutions. That's why we are just writing H1 to exist without citing a paper, of course it could be. And if all these conditions are satisfied, it means that the solution, the trivial solution, which means, and again I'll mention, which means that we assume there is a zero solution of the system, will be exponential distribution. Now an example with particular switching rules, with particular actually chosen values of the random variable, so-called sample paths of the switched system, some graphs, and finally, I think I'm time. Finally, I would like to say that I had a success in explanation the main idea about switching rules. And also, I would like to say that in the literature there are some published results about ODs, switched ODs, about many models described by ODs, switched ODs. I could say some correct, some not correct, but it doesn't matter. But nothing is done about the equations fractional. Any kind of fractional equations. Any kind of fractional plus delay. No. Any kind, as I mentioned, any kind of ODs plus random. Not talking about fractional plus random switching times. And because most of you are experts on time scales, I'm sure that it could be used on time scales. Switching rules. Switch right side of the equation. I'm feeling this. I don't know how it could be done, but this is just an idea. What could be done? And I'm absolutely sure that it could be proceed in the same way. Ideas are absolutely the same with some changes, of course. This was my presentation. Thank you for listening to me so carefully.
Questions, comments? Professor?
Discrete case?
Pardon?
Discrete case?
No, okay, in discrete case, I didn't see any published papers about switching rules.
Isn't switching in a discrete case automatic?
Well, you switch anyway all the time, but still you can, I'm sure, prove such.
Yeah, you are absolutely right. I thought about discrete case and then it didn't work because in discrete case, the right side part is every discrete time could be switched.
Yeah, but in that sense also a delay equation is not.
Yeah.
And then it destroys the whole structure.
Yes. You're absolutely right. Delays, No delays.
Okay, so let's thank the speaker again.
I have the pleasure to introduce Professor Shigi Huan, okay? And the title of his talk is Multipath Multiscale Models for Vector-Borne Disease Transmission, Heterogeneity, Mobility, and Hybrid Lagrangian Eulerian Dynamics.
Do I need this speaker? I prefer let me try. I prefer not to. Can you hear me? Yeah. First, I would like to thank the organizers, especially Jackie, for the very nice, very kind invitation. I really enjoyed my trip. Yeah. Secondly, Martin, I don't know when I met you, but I met you somewhere. Yeah.
Maybe in Wuhan.
Yeah. So welcome to the club of all boys, right? Yeah. So this is going to be based on a couple of papers joined by Leonard Schwartz and Tony Gordon, Hugh with my colleague, and of course Jackie. Very interesting, these first two authors are Brazilian students, especially Leonard is alumni of this campus. So he will be very pleased that I'm talking about something he did. This is just graduate with Miami. So first, vector-borne disease, there are many that have kind, including malaria, dengue, chikungunya, Zika, and yellow fever, and so on. Those diseases are basically transmitted by mosquitoes. So basically sometimes called mosquito-borne diseases. Vector means the mosquitoes. And those diseases represent more than 70% of all infectious diseases worldwide, in fact, and cause over 700,000 deaths every year. So it's really serious global public health problem. And it's increasing for many reasons. Because organization, global traveling like us, we travel here and going home within a couple of days, and climate change, environmental change, and so on. Use mathematical models to study this kind of vector-borne disease is not new. Starting from, probably you know that, Sir Ronald Ross, who won the Nobel Prize in 1911 in medicine. So he discovered how malaria was transmitted between mosquitoes and humans. And also he constructed a model to describe the process. The model is called Ross-McDonald model. But the classical Ross-McDonald model and all its extensions assumed homogeneous mixing between the host and the vectors. But that's important, in fact. We will see that. So in fact, the movement for mosquito and humans are slightly different from the other infectious diseases. For example, in many other infectious diseases like COVID and influenza, the movement that drives the disease spread. Because host moves and the disease spread out. Okay? Because for vector-borne disease, it's slightly different because you can introduce the passengers into new territories. Also, you connect otherwise isolated transmission zones. Okay, there's some zones there's no disease because of movement you have problems. And also, more importantly, the spread occurs across multiple spatial scales. So my models are not the dynamic models on time scale, but rather it's kind of spatial scales. So the scale could be from neighborhood to neighborhood, could from province to province, even could from countries to countries. So you can see that the movement can spread by connecting regions. Because there's a paper in Science found out human travels has been linked to maintaining malaria persistence in regions where some locations malaria is not a big problem, but because you have the international movement, it becomes a problem. But also, it could be the other way around. There's another paper published in Journal Infectious Diseases during the COVID-19 lockdown, because some people are reduced, restricted at home. In fact, that caused outbreaks of mosquito, outbreaks of dengue in some areas. So reduce travel, in fact, it can cause problems for vector-borne disease. This is something very strange. So we're going to expand that. So the question for us is how to model the effect of the hosts and vectors. and how to model it. But before doing that, we needed to understand the infection cycles of the vector-borne diseases. For example, you have one individual who is infected, that color, and that person is bitten by the mosquito, which is healthy. Then the mosquito carries the virus or the bacteria, whatever. For us, we're talking about virus. So of course, there's an incubation delay there, about 7 days. After 7 days, the mosquito becomes infectious. Suppose the mosquito is not old enough. The mosquito needed to bite somebody else to get blood, to get sugars. So when the infected mosquito bites another human who is healthy, and that person becomes infected. There's another incubation period in human to human, which is about 10 days. After 10 days, that person becomes infected. And that person is going to infect another mosquito. That's the cycle. Okay. So the classical model, the single compartment model, takes the following structure. So for the mosquitoes, you have the susceptible, exposed, and infected. So the suspect model, the susceptible mosquitoes becomes exposed. After a certain period, they become infectious. When the infectious mosquito bites the human becomes exposed and then infectious and recover. So this is a very standard structure for the vector-borne disease model. And that's the classical model. This is well studied, but this is just a single patch. Okay, there's no structure there. Now we want to consider the movement of the mosquitoes and the humans and see how to incorporate. But before doing that, we needed to know what kind of movement we're talking about. Okay. So the starting point is from 2016. Remember in 2016, 2015, there were very large scale outbreak of Zika in Brazil, right? Because the baby had a small head. And somehow the virus managed to Florida, in Miami. So Miami had a very serious problem. There were outbreaks in the neighborhoods, Little River, Windward, and Miami Beach. If you have been in Miami, you know what the areas we're talking about. This is tourist area. The tourists all go to there because they are fun there. So the Little River is a small neighborhood there. So we're gonna divide it into different patches because the patch in fact was divided by the mosquito control guys. Because each time when they had an individual who carried the virus, they will isolate the person. They will separate one square region because the mosquito fly the whole life within a mile. So that's a problem. They put a trap in the neighborhood to trap the mosquito and then test whether the local mosquito are infected. If they do, they have to control the mosquito. That's how they do that. So that's what we're going to see later on. Okay. So if you divide this neighborhood into different patches, then you can see the humans can travel among the patches. And the patch, because it's small, the mosquito can fly among those patches as well. Okay. And then also in the same year, Zika also managed to New York. But some of the people, in fact, came from Miami, but some came from elsewhere. But if you wanted to put them together to the whole United States into consideration, you have to consider different regions. So you can see you have the local short distance movement of the mosquitoes, humans. But the mosquitoes in Miami do not fly to New York. They need the humans. So in New York, you have the same kind of regions, right? The same kind of patches. The mosquito can move between the patches. But any humans travel between the regions. So that's two different kind of scale. Local scale and non-local scale. Short scale and long distance scale. So that's what we're talking about. So there are two types of movement we are talking about. The first is called commuting. Okay, that's a temporary visiting. We have to go home, like us. We came from all around the world. But we have to go home unless, they offer me a job here. I'm going to stay here, right? Otherwise, I need to go home. So that's commuting, visiting. So like a daily walk and travel. The second type is migration. Okay, if you really like it, I'm gonna move my whole family here. I'm gonna stay here. So that's a permanent relocation. That could be because of relocation organization. So basically, we're talking about for humans, the two type of movement. For mosquitoes, the mosquito, move with the neighborhood, can be either way. So how to classify this two type of movement? So our group have been working on this problem for years. In 2019, we published a very influential model. The first authors across the country, we have a group of 10 people from public health, mosquito control, and mathematicians, and so on. So we found that we can use ideas from fluid mechanics to term the movement. The first is called the Lagrange. So that's like a VCT, or like the daily travel. Individuals keep their home pad, but they spend some time in other pads and come back. All right. So this is like the fluid mechanics. They use the term for Lagrange. The other type is Euler. They don't follow the path. They follow the individuals. Where you go and where you go. So you follow the fluids. So that's for the rest of the chain. So basically, we have two types. These two are completely different. Because one is going to locate there. The other one, you go there and come back. If you go there, come back, you can bring virus to there, or you can bring the virus back. Seems more complicated in the first case. So now, what are we going to consider now? We consider M regions. Like this is in Miami, New York, and maybe Boston, and maybe all kind of. So you have many regions, large ones. And each region you have small patches. So the mosquito humans can move in among the patches in a region. And the humans can move from region to region to region, but the mosquito cannot.
Sitting in an airplane, you could.
Yeah, exactly, yeah. So that's the idea. So that's why we have multiple scales. Okay. Now, how to do that? First, let's add the Lagrange movement to the transmission. So we needed to introduce two parameters. pH, that's for human, that's for mosquito. So that's the fraction of time human resident in that patch K, which is different from your home. Like us, like me, we're gonna spend a week in Brazil and come back. So that's the fraction. That's very important. During that period, things are going to be happening. Okay. So because of that, then we needed to take that into consideration when we model the interaction between the mosquitoes and humans, either infected or non-infected. So this is the transmission term of the force of infection. So this is the infected mosquitoes. This is the healthy humans. Most people think this is the transmission rate, but in fact, it's a little bit more dedicated than that. Because for vector-borne diseases, you have two factors. A is the biting rate. That means if the unit is a day, how many times you are biting each day? Maybe twice, maybe 3 times. This is the probability factor of transmission per bite. Put them together, give you a transmission rate. That's the time of bite per day and the probability of transmission per bite. Okay. That's from mosquito to human. Of course, you can obtain a similar term from the infected human to mosquitoes. Okay. Now, the Lagrange is you go there, you stay a few days, and you go back. So each time for us, when we come to here, you can see we increase the number of mathematicians in this time dramatically in these few days, right? Whether we carry something or not, we change the number of humans, the number of mosquitoes, if we consider mosquito. So you have a sigma term because you came from everywhere out to Campinas. So you have the sigma here in the numerator, sigma in the denominator, and also your sigma for all the possible regions in Campinas. So does that explain to you what happened when you have the visitation? When you go away, okay, then the beta change, the P change, the fraction change. Now you put that into the model we just mentioned, a simple model to the multiple region, multiple patch model. So in the region I, patch K, then you can see you have double indexes there to the local and non-local. So you have the sigma in each one of them. But the mosquito do not move, so you don't have the sigma term for here, right? And also because this is for the Lagrange, okay? So you have to go back, so you only have this one here. So that's the first step. Then the second step, you add Euler movement. Euler movements, those people or mosquito go there and never come back. But you see, when you move there, you don't go back. You change the population dynamics in the location permanently. That's something you have to keep in mind. So you have, in fact, you change the population dynamics. We use parameters to indicate the local and other parameters for the local and non-local. Okay. So to put it this way, on top of that, for that region, between different patches, the mosquito transmitted among the small patches. So for the larger scale, you can see the humans, you have local movement of humans. Non-local movement is humans, so you have double sigmas. So we came up with this idea because of the double integral, right? So that explains, you have local and non-local. Okay. So this is the model. It looks really complicated. In fact, we have been putting this model in the grant proposal in the last 10 years. We put it in the proposal. Each one, every time we got to fund it. But I was not able to completely analyze until this time. The graduate student helped me to analyze this model. Okay. So this is the model, look like. Okay. But you can see there's two scales, short distance, long distance. Okay. It depends on what kind of patch. You can talking about international, talking about provincial, talking about your neighborhood. You can put all of them into consideration. So now, we needed to analyze mathematically. A certain patch is given a certain parameter configuration, whether it is die out or persist. So the key threshold is R0, which is called the base group, that number. So that number qualifies the average number of infections when you have the index individual into a community. For example, if I carry certain bacteria, I came to this neighborhood because the companies I will spread the bacteria to certain people. During my units, how many people I will infect? That number, that average number is going to be a base group of that number. Say, for example, if I infect at most one person, next person infect at most one person, then the disease is going to die out because less than one. If I infect 3, and then 3 infect 9, then you can see the disease die out. So that threshold is very important. Okay? So the challenge is, so you can see when R0 is greater than 1, the disease persists. When R0 is less than 1, the disease die out. That's very standard. Now the challenge is how to obtain the explicit expression for this R0 in terms of the model parameters. That's the challenge. Okay? Now if we can do that, that will help us understand how the parameters affect the transmission, how some of the important parameters describe the movement affect the R0. Unfortunately, for most of the time, this formula is not doable. So that's in the real world. Sometimes you try to consider as many scenarios as possible, but the mathematical analysis is difficult, right? But sometimes the analysis is simple, but the model is not solid resisting. So that's a trade-off there. So what we're going to do today is we're going to try to obtain conditions under which R0 can be analyzed explicitly, and try to investigate how the movement, as mentioned, locally, non-locally, affects the R0. And then identify whether the movement is going to increase or decrease R0. Okay. So first, we're going to consider the hybrid, the combined, the Lagrange Euler movements. So we're going to find the replaceable that number and then try to study the impact of dispersal. Okay. So to do that, we have a term which is called disease-free equilibrium point. That means you have populations, maybe there's no disease. That equilibrium point is a disease-free equilibrium point. Of course, that's the ideal situation. Okay. Now, the next one is to try to evaluate R0. That's a very standard therapy approach to evaluate the R0. The idea is you try to reorganize your model so that those components contribute to the infection of the disease is put in one category and move the other component in another one. Like you move fx and vx. So this make a new inflections. This is other inflection terms. So then, based on these two terms, you can construct the next generation matrix or next generation operator. From that operator, you can evaluate the R0. So for this one, we can find the Jacobi matrix at the equilibrium point, the disease-free equilibrium point. Of course, there's a lot of calculation here. Okay, Leonard did a great job to carry out the calculations. It took him a half a year to do all the calculations. And you can see there. So let me skip that. So eventually, you obtain the so-called next generation matrix, which is F times V inverse. And the spectrum radius of this matrix is your basic reproductive number. But you can see there's too many sub-matrices, so the matrix is very complicated. Analyze this matrix, in fact, is not easy. So we try to do something here. So the first result is the stability of the disease-free equilibrium point. Of course, that's very standard. When R0 is less than one, the disease-free equilibrium point is locally stable. Otherwise, it's going to be unstable. Okay. And then, of course, we want to know what happened when R0 is greater than 1. That's more important. So at least for now, we know when R0 is greater than 1, the disease-free equilibrium is unstable. However, this does not tell us what happened afterward, right? So instability of disease-free equilibrium alone does not guarantee long-term survival of the infection, does not guarantee the persistence of our patches, does not guarantee the existence of positive endemic steady states. So to obtain more information, we needed to study another property which is called uniform persistence. Okay? So uniform persistence means that the infection stayed uniform away from the extinction. That means all the components involved in infections is greater than a positive number. Of course, the linear means uniform persistence. So uniform persistence theory was very well developed in the 80s, very hot topic. So the interpretation means that if the disease is uniform persistent, that means the infection does not vanish asymptotically. All infected component remains bounded away from zero, and persist hold uniformly across the whole system. That's, in fact, that's not good, but that's what you can do. You can study the system. The endemic equilibrium says steady state that is persistent. Okay, so uniform persistent is important because it provides a way to prove that there might be a positive equilibrium point. So our result mathematically says that now if R0 is greater than 1, all the parameters are positive, and the movement is positive, and also use all the individuals spend a fraction of time in other patches. In that case, you have uniform persistence, and consequently, you have at least one positive equilibrium point or the endemic equilibrium point. Okay. Then we needed to learn a little more. We needed to study a little bit more. But more, some people just stop here. You obtain the mathematics. You can obtain it. You can publish the paper. But we have a grant, so we needed to do more. We needed to say more. So the motivation, as I mentioned, is that during the COVID, the dengue in this report reduced mobility, increased dengue in some regions. So why? What happened? So we try to characterize the behavior of the R0, try to understand when the movement in fact increases R0 or decreases R0. Well, that's a little bit subtle than it's done. Okay. So to do that, we make different kind of assumptions because we have the mixing. The mixing, you have different kind of mixing. So the proportionate mixing is individual spend fixed fraction of time. Okay, so you spend a week here, everybody spend a week here. It's different from you spend 2 days, other people spend months. Okay, so you have and also uniform, and also we assume that within all the patches the equilibrium point is the same. So in this way, by making some of the assumptions, we can simplify the expression of the R naught, so we can do some math, some interesting math. So the key idea is uniform movement plus the proportionate mixing give us a matrix. We can calculate that. So the guy inside the square root, the productive matrix can be evaluated by this way. Okay, so that's interesting. So for this product of the two m's, you can see we can simplify the eigenvalue. In fact, satisfy this equation. No, you know, all the eigenvalue, even the eigenvalue negative real part, you have stability. So we try to analyze when you're going to have eigenvalues negative or positive, so that the R naught becomes greater than 1 or less than 1. So this is a very interesting result. Because this equals 1. So you move 1 to the right-hand side, you use g of phi to represent the expression. The phi is the dispersal rate. It's the dispersal rate. So now, in other words, you obtain the function in terms of the dispersal rate or the distribution rate. You see what is going to happen. So this is obtained by setting lambda equals lambda. So the zero of this function indicates that the transmission point where the eigenvalue in fact is changing from greater than 1 to negative 1. Okay. So the function in fact is defined from the interval from 0 to 1 over delta. Delta is defined in the previous slide. So you can see you have a region here. So when phi equals 0, the system has no human dispersal. That's a special case. If phi equals 1 over delta, it's completely homogeneous. So that means everybody moves the same rate. We have special case. So our idea is try to say for each region, suppose that region R naught is greater than 1. Then you try to see whether or not the function we just mentioned have poles in the interval from 0 to 1 over delta. Okay, or cosine poles. That means you hold the boundary. Okay, so the result I can summarize as follows. So for the first case, if in the interval here you don't have any poles, so everything is below this one. Of course, R naught is the last one. So you don't have positive current point. You don't know anything about stability because it does not exist. Now, if there is a pole and especially at the boundary this is less than 1, then the guy here. So if we have value here, so that this one is, so you can see the R naught when this one is greater than 1 and becomes less than 1. Okay, so you can determine certain transmission rate, so that after this rate, before this rate, R naught is greater than 1. After this rate, R naught is less than 1. Also, if you have poles in between, then this one is always greater than 1. And finally, for the quasi pole, any time between this interval you have R naught is greater than 1. So mathematically you are able to quantify the R naught. But maybe this is a little bit difficult to understand. Let me give you a special case before. So, okay. Let me give you a special case. They might be more, a little bit easier to understand what we're talking about. So suppose we consider a simple region. For example, you can consider Campinas. You have the campus, you have the downtown, you have different patches. You try to study that. So you don't have any actual terms here. You have this two. And in this case, you can see the R naught can be obtained explicitly, right? I remember the people moving from this patch to that patch, from this neighborhood to that neighborhood. You have two types, Lagrangian and Euler. But we don't know which one you're going to take, right? So let's consider a mixture of that. So this is a parameter epsilon here, describe that. So epsilon is the fraction of time spent in the home patch. Now if epsilon equals 1, then you stay at home all the time. You never go out during the COVID. If epsilon equals 0, then you are going everywhere. You party everywhere. You're dining in this neighborhood, the next neighborhood, and the whole week. So that's two special cases. So we can prove that when n equals 2, R naught, the basic redundant, has no critical point inside the region. You have 0, 1, 0, 1. You have a rectangle. You don't have critical point inside. The most important part is this one. we take n equals from 2 to 20, we run like a 1,000 simulation. We found out the maximum and minimum of R0 occur any on the boundary. So that means either everybody's moving or everybody stay at home. You can obtain the maximum or minimum of the R0. Okay. So if you do a mixture, you do not reach the maximum minimum of the R0. Okay. So that's our simulation. So we conjecture, because the previous lemma is for n equals 2, we conjecture that for n greater than equal to 2, the maximum minimum are obtained on the boundary of this one. So anyhow, Lagrange or Euler, Lagrange or Euler, the combination doesn't give you the maximum value or minimum value. This mathematically is a very interesting result. Very interesting result. So basically, this is Leonard's thesis. Okay. Now let me switch to the second part. This is Antonia's thesis. And this is based on a paper just accepted last week, okay, by Design Journal of Applied Dynamic Systems. So we applied the idea to talking about the chikungunya, especially the special spread of chikungunya between Florida and Brazil. Okay, and that's what my grant is about. So probably we needed to mention what is chikungunya. Maybe some of you never heard about that. So chikungunya is a virus disease transmitted by mosquitoes. The mosquitoes are called Aedes mosquito. There are two types, Aedes aegypti, Aedes albopictus. I think in Brazil it's aegypti. In Miami we have both. In China we have albopictus, because albopictus originated from Southeast Asia. Okay, that's a completely different story. So this virus was first isolated in Tanzania in 1952. Okay, the symptoms including the fever, a very bad joint pain, noisy, and many times this will like misdiagnosed as dengue, but in fact it's not. It's chikungunya. Chikungunya affects senior people. When the senior people get infected, they walk like this way. So that's exactly the word means. The word is came from the native town in Tanzania. Means the person getting infected is walking like that. It means chikungunya. The word means chikungunya is that way. So there was silence for a long time, but in 2004, the outbreak in Kenya subsequently spread to the Luang and the Indian Ocean Island, India, Sri Lanka, and so on. In 2013, somehow it spread to Central America and then South America. It becomes a huge problem in Brazil. Okay. Like Brazil in 2024 has more than 250 cases. Last year it's 129 cases. That's the death. So this is a very serious problem here. Okay. So I show you the map. So in 2004, in Kenya was outbreak happened here. So in 2025 to the island in the ocean and spread managed to India. So in 2007 it was very bad in India, and then spread to Italy and France, but at the same time to Southeast Asia, from Southeast Asia to Central America, and managed to here in 2014. Now becomes local in South and Central America. Okay. So we're going to use the same idea to model the chikungunya, expect between Brazil and Florida. Now what happened in Florida? Now before 2006, all the cases in Florida, United States were travelers. Okay, they came from somewhere else. But in 2014, somehow there's a local outbreak in Florida. Any small number, but that's very serious. You have local cases, means those people got infected. They never left Florida, means they came from some travelers came to Florida. Those travelers infect local mosquitoes. The local mosquito bite the local people. That becomes a problem. Okay, so that's the figure, that's the data. So here, because we are considering specific problems, we need to consider more features. For example, you need to consider temperatures. Okay, in Florida, in Brazil, temperature is really important for the climate, for many other factors. Our vertical transmission for chikungunya is very serious. The infected mosquito lay eggs. The legs carry the virus. When the legs develop to mosquitoes, the mosquito carries the virus automatically. Okay. and of humans, okay? And now the time delays, as I mentioned, you have time delays. And also the time delays within the mosquito and human change along the temperatures too. They make things more complicated. The delay is not constant, depends on time. So to reflect this is that all the parameters are periodic functions. So that makes things much more complicated. So this is the structure of the model. So you have the larva. Some larvae are healthy, some larvae are infected. They are the eggs of the infected mosquito. So they were developed to infect mosquitoes. And the mosquito get infected because they bite infected humans, okay? And the healthy humans bite bitten by local mosquito, infected mosquitoes get infected. So this is the diagram, okay? But the point is that all the coefficients are time period that depend on temperature, okay? So this is the model. So for the larva and mosquito, you can see the model is really ugly. It's very complicated. You have the coefficient depends on time. You have the delay depends on time, and you have the input term taking care of the delay and so on, right? And this is for the humans also. So I will not, because of time, I was not talking about the mathematical analysis of the model. We did study the web closeness of the model. We obtain conditions between the mosquito reproduction number and the disease reproduction number. Also, we studied the threshold dynamic of the model. In other words, we found the basic reproduction R naught, determine the stability of the disease-free equilibrium point and the positive equilibrium. Remember, the positive equilibrium is a pair of solutions because the coefficients are periodical. It's much more complicated than it sounds. Also, we obtain conditions to ensure uniform persistence of the disease. Again, you can stop and publish the papers, but if you have ground, you need to do something else. So you need to simulate the data. So what we did was using real population and temperature data to determine all the temperature-dependent parameters for both Brazil and Florida, especially more specifically in Miami-Dade. Okay, and apply the two-pattern model to calibrate the data from Miami and Brazil. Okay, that in fact is a huge project. So we choose 8 states in Brazil. Why? Because these 8 states have direct flight to Miami. Okay. There are more states in Brazil, but we really are interested in this because we can obtain the flight data. Okay, all of this is already here, including, of course, including São Paulo. Yeah, São Paulo. Okay. So this region, this is where we studied in the Lancet Journal, the Lancet Regional Health Americas. Now, to determine all the coefficients is the most challenging job. Because remember, in the model, all the coefficients and time periodical depend on time. Some of the parameters that can be obtained from the literature, because there are many other people study similar problems, not chikungunya, maybe dengue or Zika. We can borrow some formulas from them. So some are obtained. You like the death rate, like the delay, you can obtain that. But some other parameters, we have to do that ourselves. So for example, we have to use linear regression to obtain a formula for the temperature development. So how the larva developed to adults. So we need a function to do that. And we obtain that. For that, and then you obtain the delay. Okay. Also, the average temperature in Brazil and Miami we can obtain. So that's 365 days. So that's the function describing how the temperature changes each day. You have to match your data with the temperature every day. It's a little bit subtle, okay? Now, so we have to buy the biting rate. The biting rate in Brazil is slightly from Miami. So in Miami, we had the lockdown. After doing the lockdown, everybody stay at home, right? Everybody within your swimming pool. You don't have the biting rate. It's different. Also, the migration, okay? The migration between these two regions, because we have data. So, because there's a website that's Visit Florida. We found that it's about 1 million people moved between Brazil and Miami from 2000 to 2023. So we try to fit them. Okay. And also you try to obtain the initial data. Also you have the delay. You can see the delay in Miami and Florida. In Miami and Brazil are different. You can see. For Brazil it's about 10.909. For Miami it's 9.51 days. Okay. So then you can see that's the simulation. So this is the data from Brazil from the year 2020 to 2024. So the blue curve is the data. The red one is the simulation, is the solution of the model. So we are able to simulate that. Very nice. Because the model can be used to simulate, to calibrate the data. Of course, then we can analyze the model again to say something, to make some recommendation, or to say what's important for the spread or control. So if we try to reduce the binding rate, so in other words, using bandwidth, using screen and so on, then you can reduce that. Of course, that's very extreme, very difficult. Also for Miami, the data is very little. So you can see if you try to reduce the bit binding rate, it can drop dramatically. The second is you can, for mosquito-borne diseases, the best way is control the mosquitoes. Okay, it's different from COVID. The COVID, you can isolate the people, you cannot kill people. But for mosquitoes, you can always kill the mosquito. But there's two ways, which is one is called a larvicide, another is adulticide. Adulticide used to kill the adult mosquitoes. Larvicide used to kill, the eggs. So you can see that's in Brazil. If you use the adult mosquito death rate, this is the larva death rate. Both can reduce the number of mosquitoes. Of course, you can reduce the transmission of the disease. That's the same thing for Miami. This is for Miami. This is for Brazil. Of course, the best is a combination. So we did simulations. You try to put several strategies together. Of course, you can reduce the R0 dramatically. So our conclusion is that reducing the mosquito biting rate is crucial to obtain a disease-free equilibrium point. And virtual transmission cannot be ignored. It's important. The movement of the human impact is a crucial factor for the disease spread from one location to another location. So maybe later on, when you try to propose something to the CDC or something, maybe you need to combine the climate change, the mobility of the humans, and so on. Right? It's very important. And also, the last one, in fact, is published in mathematician. Why so far you have chikungunya in Brazil every year, but there's not too many local cases in Miami? The key reason is because the mosquito seasons in Brazil, the mosquito season in Miami are opposite, do not overlap. So in Miami, the mosquito season on July the 1st. But what happens if global warming, our mosquito seasons start on June the 30th? What's going to happen? In this model, we show you, well, then the probability changes dramatically if the mosquito season started in Miami 1 day early. What happens if it started 10 days earlier? Nobody knows what happened or not. Okay. So Antonio did this good job, and he got a job with the CDC. Leonard is a very good modeler, so he found a job with the U.S. Bank. Okay. So that's what I'm going to talk about. Thank you very much.
Questions, comments to Professor? Have 1 minute. Okay, thank you.
Any of the theoretical results been really applied by politicians, say?
Oh, well, we do. Because we're working with the mosquito control. We have a collaboration with them.
Yes.
Yeah. Oh, yeah. We had the papers. They really follow. And some of the people we have, they are coauthors. Like control the mosquitoes in Miami. When we had data, they didn't know how to kill the mosquitoes using adulticide or larvicide, and how many days we had a model. We tell them what to do. They follow. They do. And Antonio found a job in CDC. That means they understood. They know what to do.
In my country.
So,
There's one.
I'm just curious, does the character of each batch matter? For example, there are some batches with more.
Maybe in a large scale, each patch matters because there's a link there. If you have something dramatically happen in your patch and you don't have the isolation, that will spread to next patch and then to next region. That's what happened in COVID.
And that is reflected in one of the distribution, right?
Yes. Yes. Martin, yes.
yeah, there's a possibility is there for this thing a possibility that I've heard they release like artificial mosquitoes and they and
A very good question. One method is called wall bubble. So there's like a bacteria. They infect the mosquitoes. So the mosquito lay eggs. The eggs are no longer infectious.
yeah.
But my collaborator from the public school really against that because there's too many mosquitoes there. If there's a million, there's a paper published in Science Nature shows that you have released 5 million for mosquito to control them.
Yeah, completely.
But if you miss any one of them, everything can start again. It's not economical. It's not.
Will it start again or will it change?
Well, that will be more complicated to develop resistance. To be more complicated. So my collaborator really against. He doesn't allow us to work on that.
Oh, he doesn't allow
No.
you.
Okay. So let's thank the speaker again.
Little change in the schedule, and now it's my pleasure to introduce my dear friend, Professor Everaldo Bonotto. And the title of his talk is Impulsive Dynamical Systems versus Discrete Systems, Minimality, Stability, and Recurrent Motions.
Thank you, Valeria, for the introduction. Maybe I don't need the microphone as well. If somebody don't hear me, just tell me that I can take the microphone. And at first, I'd like to thank the organizing committee, Jacqueline, Tom, Sabrina, for everything that you have done here. And I also was trying to find some picture that I had on my computer. I wasn't there because I was taking the picture, but it happened. I think this SMC summer meeting in 2019. Yes, we have the first picture here with Matufo and Martin. Here, Thomas and Martin with the ladies.
Yeah, but well, the first time I was there 2012.
12,
And
yeah.
you were always there.
Well, the first time that I met you there, yeah, I think when Jacqueline finished her PhD. Yeah, I remember that. But in the picture, I found that.
Yeah.
Oh, and effort, Martin. I'm sorry, but I'm not talking about time scales. It's not what I do. But I always tell me something that I have done with my collaborator and impulse dynamical system, but I include something about the discrete system as well. I want to show you how keeping a continuous dynamical system, I have a pulsive system, and from this system I can establish as well a discrete system. I'd like to relate some properties that happen in the discrete system and the impulsive system. This work is a joint work with Professor Daniela de Moner and Ginara. Its work is submitted, and we finished that in Seville. It's Daniela and Ginara. We did a campaign to finish that, and start another work there with Thomas Carvalho. But Thomas is in another work after that. It's done by. So I will start tell you what is the impulsive system that I work. For that, I will just recall the definition what is a continuous dynamical system. Here I consider some metric space. and they are continuous dynamical system or a dynamical system that act in a space X are represented by this triplet. It's just a map defined in the X time R plus, taking value in X, that satisfies the identity axiom, also the semi-group property, and the continuity in the both variable. It's continuous in T and also in the variable X. Okay? So I represent the trajectory of this fixed point by X, and the positive orbit you represent by this O. Given this continuous dynamical system, I want to introduce now what is the impulsive system that is dependent of a given dynamical system, and from that impulsive system I will construct a discrete system that is derived from the discontinuity of the system here. Okay? The formal definition says that an impulsive dynamical system that I represent by that X by Mi consists of a continuous dynamical system, a set M that I call the impulsive set, that is a non-empty closed set that has the following property. For every point in M, we have that. It means that the trajectory cannot walk inside of M. The trajectory needs to cross the set. So the trajectory cross, not necessarily is transversal, but it needs to cross. And the I, that's the continuous function defined in M and taking value in X, it plays the role of the impulses. I will show how it happens in the next slide. So now giving a continuous system, I will show who is the impulsive dynamical system and who is that discrete system. I start with some point X here, and I will move this point by the continuous flow pi up to it hits the set M. To what's happening here. And before to explain what's happening here, I will explain what is this function here, because it's the time when the flow hits the set M. I'm speaking about the impact function. This impact function is a map defined in X and take values in this interval. Here the function is strictly positive, and it also can assume the value infinity. In how it works, I take a point X. If the flow, the continuous flow, it didn't hit the set M between 0 and S, but at time S it hits M, it will be the value of the impact function. It means that it's the least positive time for which the trajectory hits the set M. But if the continuous flow it didn't find the set M for any t bigger than 0, it's infinity. Why I'm telling it's strictly it's bigger than 0? Because if it starts in the set M, it's not 0. This function is not 0. I need to find the smallest time, positive time for which the trajectory hits the set M. So, it's the representation of this time. Don't consider this time. That back here. If I construct the flow of the system, I will represent by tilde. Okay? But here, if fx is infinity, it means that this trajectory will not hit the set M, so I will define it by tilde t like by for every t. So it's continuous, we don't have any jump here. But if the flow hits the set M, it will happen in the time phi x, that's the smallest time for it, and you have a continuous trajectory here. So between 0 and the impact function of x, the phi tilde will be the continuous flow. But at this time here, that's in M, I use the operator y to have the first jump. It's m, I apply the function y in x1, it's jump from here. Okay? We have the first jump. So at this time, the pi tilde flow will be this time that I call x1 plus, just to simplify notation. I call this this flow here by x1 because I need some interaction. It's easier to write like that. Now the flow starts here. So I start from the continuous flow here by pi x1 plus t minus x up to it hits the set n. If it doesn't, it will be continuous. But if it hits the set n, it will occur in the impact function of this, and so on. So you have a function that the impulse is not preceded. It can happen dependent of the states. Well, we have a lot of study of this kind of flow here, but in this work, I will show that when you look the sequence here, we show that it generates a discrete system. If you consider the space, we need some hypothesis to consider that a subset of IM where we have many infinite impulses to define this map here. This map G that maps x hat to x hat, I define like that. The impulse applied just in this impact function here. So it's in the end interaction of G, it goes to xn plus. So you have already indeed here a discrete system. I will tell you something that can happen on the trajectory in the topological dynamics of the system and after that I want to show some recurrent motions that if happen in the system, I would like to know if I also have in the system. If you have the same property here, I would like to know if I can transfer this property to another system. So I will assume that the pi tilde, the trajectory is defined on all the positive real lines. It can happen to define just a short interval, but we also can give some hypothesis from it to be defined on all the positive real line here. For instance, if IM doesn't intercept M, then I consider it in almost all of the results. And if IM is compact, we can show that the flow is defined in this real line here. And here, the positive order, I put tilde to differ from the continuous system to a positive system. And although we lose now the continuity of the trajectories, it's good that this impulsive semi-flow is still satisfying the two properties of the continuous system. I mean, the identity property still holds, and the semi-group also still holds. And it's good to obtain good the topological behavior of this trajectory. So, one problem that can happen here is about the convergence of the trajectories. Here, you just consider the impulsive set like this small line here. I consider a point x that you suffer impulse when the trajectory hits here, the edge it jumps. It's a sequence that all the trajectories are continuous. So xn converges to x. If I don't consider any impulse here, by the continuity of the flow, you have this kind of convergence. But here not, because this sequence at t, you converge just to this point, that x1. But here you have a jump. So also you can lose a lot of the properties of the continuous dynamical system. But it's important to have some kind of convergence to obtain a study of a long-time behavior of impulse in the system. So the question is possible to obtain this kind of convergence here? Yes, but under some conditions. One of that is the continuity of the impact function. But since it's not continuous in general, we have a lot of examples that this function is discontinuous. The first work here in 2004 about the details, he considered some tube conditions to analyze the continuity of this function here. But the problem that the tube needs to have some open sets there, and it's hard to work in infinite dimensional spaces to prove that there are some tube conditions to work and get the continuity of this function. So in 2020, Piotr Kalita and me, we consider another approach to obtain this continuity here and avoid the tube conditions. So I consider that this function is continuous, and with this kind of continuity, we have the following convergence of impulsive flow here. And the x need to be outside of from M, because if it's M, of course we cannot have that, because one part the flow jumps, the other part not, we can lose this any property of convergence. But given a x that doesn't belong to the impulsive set in NT, if you have the sequence xn that converges to t, we can obtain a sequence beta that goes to 0 such that we have this convergence. Why do you need that beta? It happened just because in the jam. If you have some sequence that converges to x, it can happen that phi of xn, phi xn is close to m, but it's jumped, but it's not. We need some correction beta just to where this flow goes to m and jump from here. This by 2. If t it's not a jump timing, I can consider beta as 0. But if t is a jump time, we need this correction to obtain this convergence. And it's a very important result that you can use it to obtain, for example, the theory of global attractors from autonomous dynamical system. Let me tell you something about the invariance. Well, to show some result that occurs in the continuous system but doesn't occur in the impulsive system. I just remember that some set is positively invariant in the continuous system if this orbit, the positive orbit, is contained in A. In the impulsive system we have the same, just changed by all children here. If A is positively quite invariant, we know for the literature that the closure is also possess this property. But it doesn't occur in general in the impulsive system, because the set M can destroy a lot of good properties from the continuous system to the impulsive system. Here I give you some simple example. We have in the R line here, in the flow xt just x plus t. It's better right there. So here, what's happened there? The set M is just 1. Okay. If you have some point, when it's arrived to 1, here it's jumped to 0. And you have here some periodic trajectory. Okay? And if you look to this set, 0 and open 1, since it's periodic, it's positively invariant. But when you take the closure of that, the point 1, that's the point for the impulsive set, make part of this interval, and if you take this point here, since they doesn't have impulse in the time 0, the trajectory starts from here. So you lose the invariance. And the orbit of this interval now is just from 0 to infinity. So the problem here is that the points from M that destroy the good properties that we have in the continuous system. So if you have a set that's invariant, and to remove the points from M, we can show that the closure, except the points from M, is positively invariant. Now a lot of properties, when you exclude the point of M, we can show that it still holds. It's just some remark about the invariant set. Here, let me recall that we consider this system now, the discrete one, the orbit here. I will show that O hat. We have O, O tilde, and O hat. Interesting thing that I can tell you here that this set X hat is not closed in general. Here I have also some example. The trajectory of the continuous system goes to 0. I consider M here, real line times 1 with some impulse, and it goes to this line minus Q pi 2 cross 2 using this here, and it's not closed. So you cannot just use the property of discrete system in what's done in the literature, where a lot of space is closed, because it's not closed. You have to take care with that. For instance, first I didn't tell us before, but this map G here is continuous. It's just because it's a composition of continuous function, and I will consider that IM inter M is not, it's empty, because that X hat, it doesn't intercept M, so you don't have a problem of the continuity of the impactive function. Pi is continuous, I is continuous by hypothesis, but with some condition we have also continuity of that, so you have continuity of the function G. And the invariance here is the same of the discrete system as said in this space G invariant here, if the G of B hat is a subset of B hat. But since the X is not closed in general, the closure of the orbit is not invariant because it can have points outside of X hat. So if you put the intersection here in the phase space, so it's always is invariant. Okay. Before to go to the recursive properties, let me define the omega limit set from the impulsive system for this discrete system. But here, the omega limit set in the impulsive system, we define it the same way of the continuous system. And you also have the equivalence work with the sequence. We say that a point belongs to the omega limit set if you have orbiting sequence in a sequence Tn that goes to infinity, so that it goes to Y. So, of course, by the definition, it's closed. But the continuous system we have that the set is also invariant, or positively invariant. But since we can have points from M in that set, it's not invariant in general. But the limit set excluding the point of M, it's still positively invariant. We also define the limit set from the discrete system in analogs here. But here you have that this set of the discrete omega limit set is inside of the impulsive one, and it's inside of X hat. It's a closed set inside that, so we have both. It's closed and it is invariant. The invariance, okay, again happens because we don't have a problem with the set M in this space X hat. Okay, now I want to speak about some relations about some recurrent property that happen from a system and the other one. The first one is about the minimality. We know that from continuous dynamical system, minimal sets are non-empty, closed, invariant sets that doesn't contain proper subsets satisfying this property. But when you look to the system, we cannot have equilibrium in the set M, because that we need to avoid the M here. So A minus M need to be non-empty, because if it's just the set M, you cannot have minimal sets there. And now, because the M can destroy the property of invariance, we define the positive variant of the set M minus A minus M. So any minimal set here, a set that satisfies it is no empty. closed this set invariant and it doesn't contain any proper subset satisfying these three properties. For the discrete system, it's happening like what we have in the literature for the discrete system. When closed invariant and it doesn't contain any proper subset satisfying that. I would like to know if you have a minimal set in this system, if you have also a minimal set in the positive system. And also if you have a minimal system in this, if you have obtained a minimal set here. But before that, I can show it a result in another paper that say about the existence of minimal set in the positive system. Any non-empty, relatively compact positive invariant set also always contains a minimal set. We prove that from any point in A, the omega limit set exists, non-empty compact is there, and it contains a compact minimal set. So the first result is, if the discrete system contains a compact minimal set, so we can prove that the positive system also contains a compact minimal set. The catch-up proof is that, so suppose that you have a compact minimal set in the discrete system, so we prove the following result. Given some set that for every point in this set except M, we assume that the limit set is non-empty. From that, we can show the following equivalence. A is minimal in the impulsive set if and only if A is described as the impulsive omega limit set for any x that in A minus M. Proving that, we show that if you consider the closure of this orbit, you take the M of that for any point. You show that this closure is the omega limit of this point that we have here. So you can show that this set is minimal in the impulsive system. This compactness is coming from the compactness of the set here. We had implied the compactness depth. So if you have also a compact minimal set in the discrete system, you have the other one. The converse doesn't hold in general. You have here a simple example 2 in the R line that it's go to 0. I assume that here the impulsive set are the positive natural, start from 1, 1 to 3, and it jumps from n to n plus 3 over 2. We have that x hat is this infinite set here, and positively invariant set that's closed always contains a proper subset satisfy this property, because that the discrete system doesn't contain any minimal sets, but the impulsive set contains this equilibrium 0. So we have it here, but you don't have the other one. The problem is that it's unbounded this set x hat, but if you assume that for a compact minimal set here, if B hat that I define like that is non-empty in compact, so we can show that the map G applied in G and this set is compact and minimal in the discrete system. Here we have a sufficient condition to show that you have minimal set. Here you have it in the another set. And you also need to prove some result like before. I assume that if we have a point in this special set here, any set, that the omega limit is non-empty, we can show that equivalence between to be minimal and to be the omega limit set from that. So we can show that for any point of this set here, it's equal its discrete omega limit set. Because this result, we can show that it's a minimal set there. And since you have compactness here, you also have to use the continuity of G. We have that the set is continued and is compact and minimal there. So it choose just two work here, two results here to relate the minimality in both systems. Now I will tell another equivalence between some kind of stability in this system and the stability in another system. Here we work with the Zukowski stability because the stability say that the paths are together. If the data are close enough, the paths are close enough. We cannot cannot use Lyapunov stability because the jumps. For some jump can jump, the other part not. You cannot assure that this distance of the flow are closed. So a point is a quasi-stable with respect to set A. If this point is in the closure of this set, and for any epsilon, you can have a small neighborhood of this point from that for any point that in A, in the distance is small, the trajectory we can find we can find a time reparameterization that's just a homeomorphism from r plus to r plus at 0, 0. That the orbit from y is close to x. Why that? Because it can, for a lot of t, it can jump. So you need to correct the velocity of the orbit here to jump together. So because that we don't work with Lyapunov stability, that doesn't work. So this kind of you can prove that the orbits are close enough for all the t. And a point is a set possess this kind of stability if all the points possess. Okay. Just some curiosity here about this stability and the minimality. If I suppose that a point has its impulsive limit set non-empty, and when you take through the set M of the set, it's stable with respect to this orbit, we can show also that this set is minimal. So some hypothesis of stability implies the existence of minimal sets. But look into the discrete system, I consider this kind of stability, like Lyapunov stability for discrete system, but I was defining with respect to some sets to connect with the other kind of stability for the closed system. A point is stable here with respect to some set B. If for any points close enough to X, the jumps also are close enough. So I would like to see what's happening if you have some stability for the discrete system, if you can obtain the stability for the closed system, and the convert as well. But before that, here I'll also show some relation about the Lyapunov stability and the minimality set in the discrete system. If I consider the omega limit set here, non-empty, and the Lyapunov stable with respect with its orbit, we can also show that the limit set is minimal. So you can get some minimal sets in the discrete system using this kind of stability. The main result of that is the equivalence between the two kinds of stability. Here I suppose that the closure of this orbit is inside of the phase space of the discrete system, and the omega limit set, if it's Lyapunov stable with respect to its orbit of x, it's equivalent of the impulsive set except M to be so-called stable with respect to the orbit of this point. Also, you need to remove the point from M, because if you take some point M, you don't have more stability, because some point jump, others not. You lose the stability. To prove that, supposing that you have the stability here in the impulsive system, taking any point in the omega limit set, and for all point here that's close enough to P, from the Zukov stability, we can show when you take the jump point of y, it's close enough by the Zukov stability. But at this point of the jump, it's the same of the jump of y and the jump of b. So we translate the stability of the path here to the discrete system. And on the other side, it's more complicated because you need to construct the parameterization here. If you take some point here, this limit set, we need to construct some neighborhood of P, where for every point here the trajectory is close enough of P. And for that, you construct like that. You use the jumps of T with the jumps of Pn, and it controls the speed of the trajectory of y for every points just jump together. With this control, we can show that the trajectory are close enough, and you can show the stability of this set here with respect to the arc of x. And I'm finished with recurrence property. I didn't pick the strong recurrence here, but the almost recurrence of impulsive system. Here, a point is almost picture recurrent. If you give it epsilon, you can find some t, so that for all s, this interval always contains some point t, so that it's together. If you have the point x, the trajectory will pass close to x infinite many times. It will be very close to s for a lot of the sequence here. And for the discrete system, I define like that. If you always can find some n, so that for always two integers here, you can find n that belong to this integer from 0 to n, so that the jumps are close enough. So if you have some recurrence motion in the discrete, I would like to obtain for the impulsive and the converse too. Before that, just to remark some relation about recurrence and minimality in the impulsive, not in the discrete one. But if you have some compact minimal set, every point here of this x, if it's not in M, is also almost recurrent. So the compact minimal set contains a lot of recurrent motions. And if you have a point that's not in M is recurrent here, and the omega limit set is also minimal. So with that we can show that the closure of this point x also is minimal in the impulsive set. But looking for the both two results now, connecting the recurrence here and the recurrence, that if a point is almost picture recurrent in the, but no, if it's in the impulse, I take the point in x hat, but it's almost picture recurrent in the impulsive system. We can show that this point is the recurrent point. First, to show that the P1 plus is recurrent. P is just P0. If you prove the P1, you can prove to P, and there are another points as a consequence to show that all of them are recurrent. And the converse also holds, but provided that the impact function is bounded. Because if not bounded, you have counter example to show that it doesn't happen. But if you have some boundaries of the impact function, we can show that the recurrence point here in the discrete system also implies the recurrence in the impulsive dynamical system. So I think it was the last result.
Questions, comments?
It's not like
No?
not biology. The check is not in the.
Are you scared?
My students should.
Okay. So let's take it around again. Okay.
Okay, please take your seats. It's my pleasure to introduce you the group of mathematical biologists from IMEC Unicamp. They will sit on the chair here, and you are going to listen to a very interesting history about this group. I will call João Frederico Meyer, Johnny, mais conhecido, well known by Johnny. Uhul! Wilson Castro Jr. Okay, please. Estevão Esme Laurencino. Laureana. It's not my letter, sorry. Rodney Carlos Bassanete. Laércio Venditti. Laércio Carvalho de Barros. I will provide a chair for Jaqueline Mesquita, the youngest member of this nice group. Okay. Who is the first? Joe?
Can use the board
Okay, so I think I will be the chair. Oh, sorry, I will be the chair. It seems. So it's my great pleasure to give the word to Professor Johnny to talk a little about the history of the group. Thank you.
Thank you, Jacqueline. I hope everybody is fine. And this is not typical weather for Campinas. But it's good weather because in general this time is the time of a dry season, and this rain is very welcome. We had a drought some years ago when we were all all nervous about not having enough water for our evening bath. Well, I would like to. I began teaching here way back in 1971, and I believe some of you weren't born back then. And I was giving classes to 124 students, calculus. And there was the access for teachers opened the door, which was in the middle of the blackboard. It was a green board, but it was called blackboard anyway. And all of a sudden the door opened, and my fiancée gave 3 hurried steps into the room. I was teaching the kids, and Rodney, who is my sponsor, pushed her into the room, my classroom, and everybody was startled, me above all, and she didn't know what to do, and Rodney stuck his head into the classroom and says, she's the teacher's fiancée, say hello to her. Well, no more classes, no more calculus. And it was multivariate calculus, so it was a complicated class, and I couldn't do it anymore. And back in 1971, I had already been working with Rodney. We have these special grants for undergrads, and he made me study complex variables and lots of mechanics. Little did I know that I would be working with him for the rest of my life. This was in 1969, wasn't it? You had just arrived from Brasilia, and you made me and Ivanezina study the complex variables and all sorts of things in mechanics. And but imagine that. I'm sorry. Do I really need this? Yes. Love me tender, love me sweet. Well, biomathematics was born here in the early 70s. With Rodney and a professor from Chile called Alejandro Engel. And we had a national congress of applied and computational mathematics here. And Alejandro Engel wrote not a booklet, it was a heavy thing, on biomathematics with population dynamics. And Hodney had already begun studying and teaching these subjects, and I began working with Hodney. And a year later, Wilson came and joined the group. Now, Wilson is what we call, we say PhD, meaning a doctor in mathematics or in physics or whatever. But Wilson is really a philosophy doctor, because he works with the philosophy of biomathematics. And he's the person to go to when you had any doubts about anything. I remember a deceased friend of ours who worked in biomathematics called Silvio Pregnolato. And he died so early, he left us so early. And he was older than I am, but he had been teaching for less time. And he was a wonderful friend. And he was the guy who always said that if there's anything worth knowing, Wilson knows it. He's gonna speak to you, and you're gonna see the person that he is. And we began working with Hodney, and it was always applied biomathematics, not applicable biomathematics. It was applied mathematics. Applied mathematics, really, in its sense. Even though Hodney was always in the mathematics department, he was in the applied. Wilson and I were in the applied mathematics department, but Hodney was in the pure mathematics. And I don't know what pure mathematics is. I think that mathematics, which we call pure, is mathematics applied to mathematics, and like timescales, in which you use continuous focus on discrete equations. And so you apply, we started working with Hodney, and I remember that Hodney tutored a master student here called Vinicius Pereira, who then moved on to mathematics education, which he coordinates in Universidade Federal do Mato Grosso in Cuiabá. And in this very room, Vinicius showed that the International Bank demand for the construction of hydroelectric dams in Brazil, insofar as the environment was concerned, was not working, because they were collecting mammals, snakes from flooded areas and releasing them in natural forests. But that would set the population way above the carrying capacity. This was what Vinicius did. I remember perfectly. And then he said, no, this can't be done, this shouldn't be done, and it's not done anymore. And then Hodney asked me to go with him to Londrina to give a course on something. And then he made me calculate something which demanded something I'd never worked with before, which was a third-degree polynomial. I worked with polynomials of degree n, okay, and of degree 1 and 2, yeah. 3, never. And I discovered then that what biomathematics wanted with me, it wasn't for my good looks or my intelligence or anything. It was because I could do the mathematical methods, which is what I really like. And so I worked a lot with finite differences and finite elements and finite volumes and lots of computer. I am not a computer expert because they keep changing the softwares. I spoke to, where is she? She's from Maringá, where is she? Oh, there you are. And she's working with a language called Julia. But I'm with an old Fortran group, a MATLAB group, and that's what I make my students use, because we use Octave, in fact, because it's free. And Wilson Ferreira was a big contribution, like Hodney. Hodney had lots of international contacts, mostly in Europe, in Italy. And Wilson had lots of contacts in the U.S. And so he was responsible for bringing some of the people here. And he made Lee Sego come, and he came back from University of Washington with lots of ideas, and of course he influenced me. He's younger than I am, but he was a great influence and a source of motivation for me. And here in Brazil, you are forced to retire when you turn, in public service, you are forced to retire if you turn 75. And I turned 75, and as a retiree, you can do what you want. And I like giving classes, and I like doing research. I'm a volunteer here. And Laércio came after. Laércio in the blue suit, in the blue tracksuit, came after, and he was an important addition because he liked working with the physiological aspects of biomathematics. He has a patent included. You're going to talk about it. You can talk about it. But he's another guy who was my client because he would come up with these problems in cancer, and they would need numerical methods. So they all came to, between quotation marks, they all fell in love with me. Not with me, but with the answers I could provide them. And until today, I work with numerical methods for nonlinear systems of PDEs. And our newest addition to the group, which is not Jacqueline anymore, it's now Beatriz Laiati, and she is making me use Beatriz Laiati. Just raise your arm, please, Beatriz. Raise your arm. Thank you. That's her. She is the newest, and we only had men, which didn't account for much good humor. But now we have two beautiful women, and both are mad. You know, they get mad. Not mad crazy. They get mad angry easily. So we have to cut the line. Then we had Esteban came along, like Beatriz, working with Rodney, and these fuzzy aspects. And then I had to work with numerical methods with fuzzy as well, because Professor Eleni, she is Unicamp as well, but she works more in the area of environmental impact. And she has been working with environmental impact in dams in our region. And she uses fuzzy parameters. And Esteban is the specialist in fuzziness. And we had Marcus, who was my student many years ago, but he recently left biomathematics, and he works on numerical methods on his own. But he moved to fuzziness. But we also have Felipe, which is sitting next to Beatriz, and we have Juliana Marta, which is also a postdoc student of ours, and Juliana Marta did a very good work for our group when she modeled the growth of COVID in Portugal, and one of her equations was very off because of the non-notification. It was terrible. What's the matter? Maybe the microphones are afraid I'll sing again. We have had, you don't have to believe this, but it's in our data. We have had hundreds of students. In one level means we have a grant for undergraduates. And they have 1 year in which they develop some sort of project with some teacher. And this is financed by the university, by our national council, and by our state entity for financing research, FAPESP. And we have had hundreds of students. And Rodney has already tutored more than 100 dissertations and theses. And I'm on my way. I won't reach him, but I'm on my way there. And also we have ex-students in most of Brazil, and we have ex-students in many places in Latin America. And we have one in Canada, and we have Serginho in the US, if he's still at Princeton, I don't know. but we have students in many places. Luckily, we are not the most important biomathematics group anymore because these students have taken flight on their own and have created their own groups. Laércio therefore works more with the physiological aspects. I work with mathematical ecology. Mathematical ecology is, some people say it's a transdisciplinary approach to nature and society, but I believe sincerely that it's an antidisciplinary approach to science, because we cannot study dengue, for example, without studying global change and warming and El Nino, which is going to make it very rainy and which is global impact. And we can't study epidemiology without considering population dynamics. And we see these models which were famous until some years ago, in which the population received a constant addition. And so we had dPdt is equal to some big P, and then the rest of the equation, because it was easier to solve. Maybe they didn't have a slave to do the numerical methods for them. Christian, who did his doctorate here, worked with population dynamics and AIDS, which shows the non-disciplinary approach to working in biomathematics and mathematical ecology, which is what we do. We have researchers in Botucatu. We have quite a lot of researchers in Botucatu. We have Graciele, we have Magda, we have Paulo Mancera, and we have Rovida, him and her, Sandra Rovida, and Flávio Rovida. So we have a place, and Cantão is there too. So a place with, Cantão worked with me with environmental impact. So they have a group. They can create a group of theirs they do not depend upon us. That's why I said that we were important in the past, but because of these students, young, intelligent, full of energy, they don't need us anymore. And we have students in Minas Gerais, Rio de Janeiro, Rio Grande do Sul, in Santa Maria, and in Porto Alegre, in Mato Grosso do Sul, and I teach calculus to 127 students. So can I speak like this? If I okay.
Let's try one second. I don't know what's happening.
And so that is the introduction I was to make on our group. I decided not to make a formal presentation because that would mean putting names up there and subjects. But what I would like to stress is that we have always tried to work with applied biomathematics and mathematical ecology. We have tried to solve problems which come from nature and which come from society. And Rodney had a very inspiring situation in which he tutored a young lady who studied the cancer that came to kill her not too long after she presented her doctoral thesis. And it was an example of resilience, of hard work, of dedication, and she is still an inspiration to most of our students. And that's who we are. Okay? That's it. Any questions?
Thank you very much for bringing us about the history. I don't know, some questions? We open for questions, then we call the next one. So, questions?
Questions?
Yeah, I mean, just what, can you give like a couple of examples where people in that institute are working on?
Yes. Well, let's start with, I don't know about Rodney, but Laércio is working with environmental impact as well in cross diffusion, and I don't know. Wilson always does everything, but he's also retired. And Laércio works with fuzzy techniques, and we can't run away from fuzziness. I have a very serious health situation. There are so many things I can't do. I can't run up this. I can't do anything because I have had an aneurysm in my whole aorta. The inner part is just blown open. So I have a small. But the doctor says you have to measure your blood pressure and your heart rate frequency every so many days. And so I'd measure 5 times, and then I'd get neither of with 15-second interval, and all the numbers were different. All the numbers were different, and I get the mean, and the mean was also different. So there's no way that we can work with the beautiful, exact, and true mathematics. We have to work with fuzzy mathematics. And to work it all off, I work with numerical methods. and I work with numerical methods, so I don't mind these complicated problems because, and then we have Stevo, who is working with, who is doing what I need to learn. I'm going to be 80 next year, and there are so many things for me to learn still. I want to work with numerical methods in his instruments, in partial differential equation, in fuzzy Banach spaces, which Beatrice is working on. So that's what we do. But if you have a problem, if you have a if you have any problem in biomathematics,
The intervals are getting
Jacqueline thinks I'm turning it off. If anybody has a problem, bring it to us, which has made Rodney work with practically everything that can relate to biomathematics and to give me work to do. So ever since that third degree polynomial back in 1974 in Lodrina, he's always giving me a hard time. Best man in my marriage, and I have to respect his Now can I sing? No more questions? Well, I can tell you that working with Rodney is we always do it his way. Instead of saying my way, I can say his way, which is Rodney's a very special reference.
More questions? Sorry, more questions. More questions or comments? Okay, if not, so let's thank you very much, John, again. So now I will invite Professor Wilson to... Esteban told me that's you.
So I have my frame in Portuguese, so I will talk in Portuguese. Sorry about that. Frame is on. Frame. Okay, and also, can I use this? dele. O slide eu acho que vai ser legível também para quem não fala português. Bom, a ideia é o seguinte, eu tive que remanejar o meu talk, porque eu imaginava outro tipo de audiência, mas eu acho que eu posso me adaptar a essa audiência. Oi? Ok. Well, as you can see from the slide, I'm talking ruminations about biomath, math bio. Why biomath and math bio? That's the first question. What kind of subject is biomath and math bio? Well, this is a picture which we took in 1989 with Professor B.C. This guy here. Fortunately, he left us about 10 years, 12 years ago. And he was very influential as to what kind of mathematics and what kind of approach we had in mathematics here. I could say that for me, but not for others, but it's very influential. He was very influential in what I had to do and how I had to do biomathematics. And I'll talk about that. This is one of the founding books of mathematical biology that was published in 1989, the first edition. And the second edition was... The second edition came in 2000, and then the third edition, I guess, was 2010, about 2,000 pages of mathematical biology. Jim Murray, I worked with him in my postdoc in Seattle, University of Washington, west of the United States. And the second book, which I could mention here, was a book by Lee Siegel. It was called The Primer of Mathematical Biology. He wrote the first book, and then this was the second book, was published, I think, in 2015, around that. But he was already dead. And so his student, Leigh Edelstein Cashett, which is well known in biomathematics, gathered everything he wrote and published this book. He was co-authored by her, but I couldn't find it. It's a primer of mathematical biology. So those are two books which we would say that they founded the discipline of biomathematics. Not that we didn't have biomathematics before that. Okay, we had Euler did working on demographics, and Alfred Lotka worked on also demographics, and epidemiology also was working. Huxley did work on neurophysiology, and Aaron Turing wrote a paper in 1950 about morphogenesis, which was a founding paper on what came after that, and this is as you can see on this page here, you can see the jaguar, the skull, it's very morphogenic both, and one of the articles which Jim Murray wrote before writing this book was how the jaguar got his coat. And that's a kind of morphogenics. It's one of the basic problems in biology. Morphogenics is how things get together and make up a very structured situation. You have, for example, you have a very not well-formed dilution, and then suddenly the dynamics go on and you came up with an emergent structure. And this is a very interesting problem which nobody knew how to approach it. And Alan Turing, who was not the biomathematics, why not the biology, you may know him about the enigma, decipheration of enigma, and about the movie that was made in his life. And he is also important on Turing machines, etc., in many other fields, but not on biology. And he wrote two papers on biology. The one was on morphogenesis, 1950. That paper, which gave the first poster on the mathematics at that time. Two guys came from the same field to work in biomathematics. Jim Murray and Lee Siegel. And they came from fluid dynamics. They worked on fluid dynamics before 1960. And why they came to biomathematics? Because fluid dynamics you use kind of the same kind of mathematical techniques that you use in population dynamics. And that's why you use the same approach which you had very efficiently used in fluid dynamics. You can come to population dynamics. So this is the origin of the biomathematics of this at this time in 1970. I like to see this. This is a book which was written by Siegel and Lin. Lin was his advisor at MIT, and Lin was an astrophysicist, and he was one of the guys using the same techniques, fluid dynamic techniques. He showed that some galaxies, which are populations of stars, the individuals are stars, they go like spirals, like the Via Láctea. And the same techniques were used by Lee Siegel later, his student in mathematical biology, to study the dynamics of taxis, chemotaxis. And the chemotaxis is the way of how organisms go through the gradients of nutrients, for example, how they come out of the steepest point of the nutrients concentration. And he used the same techniques. And that's very interesting because the population here, you have a population of amoeba and population of chemical substance, so molecules. And after you have the population of stars. So you can see the scale. If you are talking about scale, you can see the same approach, the same mathematics, which is useful for populations of amoebas and concentration of substance, and also for population of stars. And it produced the same results. And he showed that you can have also spirals as waves of approximation that the amoebas use to approach the highest concentration of nutrients. Well, so this is I call the synthesis. Mathematics is very simple. This is a very, I like this cartoon because somebody's professor has written equation, found it. And one student, I like to see the other face of the other student. They are stone faced. They don't move. Why? Because they are conformists. The question is not an idiot question. It's a dull question. It's a valid question. But the other don't have the courage to ask. They are conformists. That's a very big problem in our media, where people are usually very conformist. They are used to submit to the authority. And they don't ask questions because they are afraid of being seen as unknowable on the subject. This is a very nice one. So what is I have to go to. So biomathematics is a mixture of biology and mathematics. So I will say it's biology. John Tyler Bohner, who was a very famous biologist, said biology is a wet science. You can understand why he said that. And Bertrand Russell was a famous mathematician, said mathematics is a very abstract and dry science. You don't know what you are talking about and how you are talking about. So how can you mix two things so different? Biology, which is very wet, and mathematics, which is very dry. How can you mix them? Well, you can do it. And that comes with the definition. Somebody asked the famous applied mathematician Joseph Keller, who was his student a long time ago, what is applied mathematics? He said, applied mathematics is a science which has mathematics as one of sub-science, and everything the rest of the universe. And that's right, because in applied mathematics you don't choose what beforehand, what you are going to apply, you're going to use, where you're going to use, and not what you are going to use. Use whatever you can in mathematics. Of course, differential equation is very useful. That's not the only thing. So I like this kind of definition, which has no boundary for anything. And mathematical models are exactly what we use to study the application. What's the mathematical models? They are bridges between the other science, let's say in this case biology, and mathematics on the other side. But it's a bridge of two ways. One way from mathematics to biology, one way from biology to mathematics. How come that? We are used to say mathematical biology. Mathematical biology means the focus is on biology. The method is mathematics. But there is also biological mathematics, which means the focus is the problem in mathematics and the ideas are from biology. I can give you many examples. Artificial intelligence is one of them. Genetic algorithm and algorithms. There are many of those situations. So we have a mathematical model, you have a two-way bridge which connects one part of biology, one part of mathematics. You can go to one way or the other way. You can solve mathematical problems using biological ideas. You never have to, are not supposed to go to biology with a toolbox and say, now I'm going to solve problems in biology. Now I can solve problems in mathematics also with tools in biology. We always have, that's what I was talking about, the biomath. And just to say, what's a kind of mathematical biology, what kind of mathematical model do we have? George Box was a statistician, English one. He said that all mathematical models are wrong, but some are useful. The problem is to know when and how to use them. And Lee Siegel used also a paraphrase from Picasso and said, mathematical model is a lie. It's an assumed lie, which helps us to see the truth. And that's right. That's what Picasso said about art. The art is a lie, which helps us to see the truth. And mathematical models are exactly that. If you ask the mathematical model to describe the reality ipsis litteris, you are out of place. It describes one of the face of the truth, but not everything. Well, I plan to say a lot about that. The first, where did applied mathematics begin? Applied mathematics began with Galileo. That's I can say that with some certainty. And because Galileo brought an analytical method, which means we are going to focus on one aspect of the reality, not everything, like a better philosophical stone, which wants to explain everything at once. We are just want to explain this part. An example was exactly what he did with studying the gravity. He went to the Pisa Tower and dropped stones. Pisa Tower. And how he did? He made that experiments. His students measured the altitude and measured the time which the stone was passing to that point. He had a table with many values of experimentation. And what that used, well, it's lots of numbers. Lots of numbers which says almost nothing. His idea was how to transform this in a synthesis so that I can use it later in other experiments. And that's what they call olhos de lince. Olhos means eyes of lince. Lince is a jaguar. In the Academy in Licey, Italy, they are proud to say that they can see more than the other people, so they're called Academia dei Lincei, which means Academy of the people who can see better than the others. They are proud of it. Probably Galileo certainly was one of them, or the most. And what he did was to use his knowledge of function. Function was not a very specific or very well-defined idea at that moment, but he knew about the functions of quadratic functions. And so he saw the table and said, well, I can write this as a quadratic function. When he wrote this as a quadratic function, he substituted the enormous amount of table, many numbers, to just two numbers, or one number actually, one constant, h equal constant t squared. So with that small piece of mathematics, he can describe all his table, his experimental table, not only this one, but the interstitial times, and the later experiments also. So this was a kind of synthesis of, which I call the oleo de lince, eyes. But you can look and find a function which represents that table. Of course, you can make a polynomial interpolation. Then you substitute, let's say if you have 20 values, and then you substitute 20 values of the table, the polynomial with 21 coefficients. What you gain with that? Almost nothing. You have no idea of what kind of physical meaning has all those coefficients. You just make interpolation. That's very interesting because it has a parallel with the problem of Ptolemy and Copernicus. Ptolemy has a very efficient way to describe the ephemerides at that point. That was not wrong. Ptolemy's model of the sky was very efficient and very good for the church to find the times of the feast and everything. But then came Copernicus, which was not better than Ptolemy. When another event appeared, they just changed the model of Ptolemy, and then you could preview all the ephemerides. And Copernicus also. So you can't make difference among them, between them, just by the efficiency of the forecasting. But there is one aspect of the difference between the Copernicus and the Ptolemy. Ptolemy was very complicated. Almost nobody could understand that. Just Ptolemy and his students probably. The other way, Copernicus, you could understand that. It was very simple. And so why Galileo preferred Copernicus? Not because it was more efficient than Ptolemy, but because it was simple, much simple. And that was one of the key questions here. It's the principle of simplicity, let's say, which is called the principle of William Owen, philosopher in the 13th century or 14th century. And he said, if you have two explanations which explain well one phenomenon, choose the simple one, not the more complicated. Choose the simpler one. It's very interesting. That's one of the explanation of why Galileo preferred Copernicus instead of Ptolemy. Not because it was more efficient, but because it was more simple. If you have a simpler model, you can work on it, make it more complicated if necessary, but then you have more control. And the other one you don't have control because it's an enormous, very elaborate model. Well, and how Galileo, what was the idea of Galileo to make a mathematical model? It was exactly that. You have experimentation, you have all the data, and then you transform this data, synthesis, make a synthetical approach to this data using a function which was a way of correlate the measures of the main observation that you have in that model. So you use a function to describe the same thing, which is a very syntactical way. I'm not talking about this, but you don't have. Oh, in the first example about the model models, if you open a book of calculus, for example, the first page of differential equation, you find differential equations, Malthusian differential equation, which is something like this. Or maybe it was this here. And immediately you say, well, I can solve this. Right? So you turn the page and forget about it. Well, that's not what a biomathematics should confront the model of Malthus. Actually, this is not exactly how the model came out. The model came out exactly the same way as the model of Galileo for the falling of the star. The model came from the table of John Grout in 1966, model of mortality. He had a table of people normal beginning with N0, 3, and then the time he was collecting how many were still alive. And he had something like that. And here comes a very interesting aspect also of mathematical model. If I write something like this, immediately you say, well, there is a curve, very explicit curve here. There is no curve here. Where can you find a curve? Well, I can see a curve here. Well, you can see, why you can see a curve here? I would say, well, I can see this curve here. Not that curve that you are seeing here. Same thing that if I write something like that. Almost everybody will see a triangle here, but I didn't draw a triangle. There's no triangle here, but you see a triangle. If you don't see a triangle, call your psychologist because you may have a problem. Everybody sees a triangle, but there's no triangle here. And that's what Canissa, Gaetano Canissa, very famous Italian psychologist, said that our brain is trained to fill up the place. So you pick what you see and turn it on something simpler than that. It's very complicated here, but if you think a triangle is a very well known. So you can transform one very complicated data to a very simple data. So our brain is a mathematical modeling instrument. Here is the same thing. When you see a curve here, you're very comfortable psychologically to see a curve. And that's why we use the differentiable function as a representation of population dynamics. Because I have taught biomathematics for 30 years, and never one student would ask me, why are you using a differential equation when n of t designates a population which is obviously a function with values, integer values? How can you use a differential equation? It's completely wrong, you could say. Nobody asked me that. Nobody raised his hand and said, how can you use this? This function is not differentiable. How do you use the differentiable function to determine a function which is not differentiable? Well, there is no proof of that. You can prove that you can, but you have the obligation to explain this, why you use. One explanation is psychological. It's because you are very comfortable psychologically to designate a differential proof. And if you use that, which is not a proof that it will work, the proof will come after you apply that. If you apply that and that gives you good results, okay, that's the proof that the model is good. There is no other proof of that. There is no mathematical proof that the mathematical model is the right mathematical model. The only proof that you have is using it. After you use it, if you try it, then you can argue. Don't prove, but you can argue that the mathematical model is appropriate. And this was you must have some explanations, evidence, not proof, but evidence. Why use a differential function to designate a model of a population like that? Well, when they had that table, they asked Christian Huygens, who was a very knowledgeable guy about verbs, and he could not find a verb which would fit. But then Leonard Euler, he invented the explanation function. He was the inventor. He invented the explanation function. You see that well-known limit as a series or a limit of 1 plus x over n, the power of n, limit of n. So he already knew that function. When he looked at that function and looked at the table, he said, I have a function which fits well in this. Not exactly. It's not an interpolation, but fits well. It's this curve here. So he used exactly the same idea of Galileo. Olio de Lince, Lince's eye. He looked at the curve and said, I know which curve is this one. Because our eye is not very good to discriminate curve. If I draw a curve like that and ask you what kind of curve, you say, well, that's a parabola. Well, it may not be a parabola, maybe a x4. Maybe something like x4, x8, x10, or a kind of sine or trigonometric, something like that. We can't distinguish that with our eye. The only curve that we can distinguish exactly with the eye, two curves, is the line. I said, this is a line. You said, well, we can say that's a line. And the circle. That by visual inspection, not by proof, by visual inspection. You can say that this is a line, and this is not a line, of course. Right? But then you can, what kind of curve is this? I don't know. I have no idea. What about this? I have no idea. It looks like a parabola, but it may not be a parabola. So, when Euler found this similarity of the graph of this function and this table, he said, well, I substituted, I don't know how many numbers you have here, maybe 200 numbers here, to how many? 2 numbers. So with only 2 numbers, you can describe the same table that John Grout used 200 to how many numbers I don't know. Well, that's a very synthetic way to describe that. And that's how mathematical models was. Just to describe a very complicated situation in a very synthetic way. And then when he saw this, he said, well, this is not the way to describe this function. The way to describe this function is to say that the solution of differential equation. Because before that, you use it. People use let's say, function tech. How many functions do you know? You know the elementary functions, the algebraic functions, trigonometric functions, exponential functions, and what else? Well, just that. But when you can use differential equation, that you expand considerably the universal function that you can represent. And that's why we use differential equation to model. It's not that we are fixed, we are determined to use differential equation. It's that we need a function as a synthesis of experiments. And this function probably is represented as a solution of differential equation. So differential equation is not the model, it's a mean to obtain the model. The model is a function. The model here is this function n of t and b in n0. This is the model. This is the mathematical model, not the differential equation. Differential equation is a way to get there. But the model is exactly the function. So, but the differential equation, this is the Newtonian method to describe functions. How? To write the functions as solutions of differential equations. And then you expand, consider the universal function that you can describe your well, still, beside the Kali's effect, we have also the Weber factor, but I'm not talking about that. But the next point is the following. Okay, you can write this table with a function which has two parameters, n0 and me and t. But then you have to biologize your solution. How is biologize? Biologize means what means n0? Well, that's very obvious. It's the population, initial population. It's very obvious. The biological meaning of n0 is the population where you begin with. But then what about this one? What's the biological meaning of me? If you're a mathematician, you don't give a damn about that. That's a me. That's a number. You just write the function, and the function is already given. But if you are a mathematical biologist, you want to know what the me is in biology. It's not very complicated to find out that the dimension, the unit of this is time. So there must be a time related. This 1/b must be a time. What kind of time you can find here? And you can make some very simple calculation and find that this is the mean time of survival of the individuals. Mean time of survival. That's a biological meaning for this parameter. If you don't know the biological meaning, you know nothing about the biological representation of this model. So it's not sufficient for you to write the solution of this. It's very interesting to know that it's not from here that problems start. It's from here. And then he wrote as a solution of differential equation because that's the Newtonian way of doing it. Well, when you look at the Malthus, I'm talking still about the Malthus problem, which is a very simple problem, which you can use one page of your calculus book to look at it. But if you look at the Malthus model for mortality, for example, you see that there are four conditions on this model. First, that it's homogeneous. Everybody is the same. They are all the same. You can distinguish elements from one to the other. This is one of the conditions. The second condition is that they don't interact between them, among them. There are no interactions among them. The third question is that there is no external influence on the mortality of those individuals. Just die. You don't say that die for that, or if somebody else shoot them. And there is a fourth, which is very important. They are a limit model. What kind of limit? It's a population of infinite number of individuals. How come? It's a population of infinite number. If you have nt is a finite number. Is that because you have a very large population, but your unity is very large? It's like you're measure a crop of rice, for example. You can measure grain for grain, but that's not the usual way. You can measure the crop of rice by sacks, by trucks of rice. You have many units. So when you write a population, you can use the very large unit so that the total population is represented by a very small number. For example, the population of Brazil, let's say it's 200 million people. You don't have to say it's 200 million. Count each head. You say it's 2 units. Which unit? 10 to the 8th. 10 to the 8th is a unit of population. Then you use number 2. It's very more manageable than using 200 million inhabitants. So there are four conditions in the Malthus model. First is homogeneity. Second is autonomy. They don't have influence of anybody. The third is that they don't interact. And the second is the limit problem. It's the limit. You are using a limit. How come you use a limit? That's a very other question, interesting question here. When you say that this is a circle, of course this is not a circle. What I am using is a circle with a perfect limit to represent that. You don't approach the approximation. The approximation is there. What's around it is approached by that value. So when you have a limit model, the limit model is put in the same place. If you have populations, very large populations, they are around that value, which is an infinite case. So you don't approach with your model the reality. The reality approach your model. That's a very different way to talk about this problem. So when you do this, you can reevaluate this. Imagine you have a large populations of individuals in Matthew's population, and you look at one. You are not interested now in large population, but in small population. Look at one individual and take a look at how many of them, or how the individual will, if he will die or not in the interval from 0 to t. One of them. Well, you have many, how many experiments you have? N0 experiments. You have N0 individuals there. You look at one and the other, they are all the same, homogeneous. They don't interact. There is no influence external. So you can make this definition of probability by frequency and say, what's the probability of survival during this period from 0 to t? How many survived? From how many? Is that value? So e to the power of minus v, t, is the probability of survival. It's another interpretation of Malthus problem. If you use how many died, so the probability of survival is 0 as you goes t to infinity. And this way here, you can see the probability of dying in this, because you had died of N0 experiments, those died from the N0, so the frequency definition of probability is that one. So, and you have a small interval, you can use it. This is exactly the Poisson model. So the Malthus model, which is written in just one page in the calculus book, has much more in it than it's written there. If you are a mathematical biologist, if you are a mathematician, you just turn the page and go the page and go to the next problem. Now, if you have a finite population, you can use the Malthus model. Why you can use the Malthus model? Because a finite population is very far from the limit case. But then you can use the interpretation, probabilistic interpretation. And then you can represent not the value of the population, but the probability of being 0, being 1, and 0, 19. And then with that last equation, which I showed in the last here, you can write the Kolmogorov equation. So that's a very nice way to bring up the Kolmogorov equation for those. As you can see, it's very much difficult, much more difficult to study finite populations of Malthusian elements than to study the limit case. You can go back in the other way. You can use a Poisson problem and then find the population model, Malthus population model, using the limit case of a medium-sized population. So this is just a way of showing that the Malthus population is a minimum, which means the more simple than you can have population dynamics. It's very easy to argue about that. That's a simpler model that you can construct for a population. So it's a minimum. If you are going anywhere else, you have to begin from the minimum. If you don't understand the Malthus model, you can go anywhere else, because that's the basic one. And those are the conditions. And the next, what we are going to do next? Relax these conditions. kind of condition, we're relaxed. Well, the limit, we already did it. Then you use it, then you come up with the probability model. The homogeneity, that's the next one. How do you write a population which is not homogeneous? And that's the next guy, Euler. Euler again. Euler came up again with the idea of how to describe a population which is not homogeneous. Homogeneous with respect to a measure. Let's say age, let's say height, whatever. What do you use to describe that? Newtonian mechanics was written for particles, point particles. And if you have gravity, two point particles in gravity, you can have the Kepler problem, which you can solve by elementary function. You have three problems: Earth, Moon, and the Sun. You can solve many questions. You can answer many questions. There is a solution, elementary solution. And you can solve it with respect to many questions. For example, if they will collide, all of them collide. So with three, you already are in problem. Imagine if you are with liquid, which have 10 to the, let's say, 40 particles. How do you describe that? Nobody knew how to do that. Who came out with an idea was Euler. He came out with the idea of distribution. That's a very interesting situation because distribution, which seems to be a very simple thing, is not very simple. It's very complicated, sophisticated way to write a function or to write a model. And it's very interesting to see that when you write a distribution or a density, you don't designate the values of the density in each point. What you designate is how it works out, how it behaves under the signal of integral. The Dirichlet way to define a function is each x, you give value of f of x. This way of which Euler introduced, you don't define f by the values of each point. You define f by the values under the integral. That's a very sophisticated way, which was introduced in formal mathematics only 200 years later with the theory of distribution, generalized functions. But that was exactly the idea that Euler introduced when he wrote the equations for the non-homogeneous population. Well, I don't dwell on that. Let me go. But then you have to write a mathematical model for these inequalities, this function, this unknown, it's the density. And for that you have, then comes the, I'm not going to talk about that, but then comes the equation of conservation. This is the equation of conservation. J is the flux, F source function, O is the density. That's the general equation which you can, from this equation, general equation which was came up with Euler, you can deduce almost all equations that we have in distributed population. So, final question. How do you find your function when you have data? You have data and you want to find a function. Well, you have many tricks. Lindsay eyes is one of them, but that's very limited. You have to be a very knowable guy about functions and have a very keen eye to find the function which adapts to that table, that large number. Today you don't have a table of 200 numbers, you have a table of 2 billion numbers, because experiments today and the capacity of bringing out data is enormous. So the Lindsay eye method is not available. So what do you do? Well, that's the next chapter of mathematical biology. To bring the synthesis of a representation of a phenomenon which you have by the data, but then you have to bring all this data to one very simple equation. How do you find this equation? Well, there are some methods now being developed, called DDM, data-driven models, and as a reference. So I think that the next generation, if I was to begin here in mathematical biology, I would try to find out how those people are doing this. How you find a differential equation which just a few parameters would describe a phenomenon which has given you through a table, a Normals table of data. How do you describe that with just a few parameters? Well, that's the data-driven models. That's the next chapter of mathematical biology, as I see it. So let me finish here by giving this reference if anybody wants to see what I'm talking about. This book of Brunton, which they are from the University of Washington, Seattle. Very noble. Okay, thank you.
Thank you very much for this very nice talk and introduction. Explain all these things. Very interesting. Thank you. Any questions or comments? Okay, if not, so now I will invite the last to talk a little about the group. Esteban, please. Okay, so it's my great pleasure to introduce also Professor Estevão Laureano that also works here in the group. So, Estevão, the floor is yours.
Thank you. I will try to be short here. Let's see. Different of my colleagues, I will try to be more technical here, and as you see, they have 40 years of experience in the biomathematics. You have a lot of contributions in different areas, but I would like to show something connected with fractional calculus. So that is the result here is part of PDTs devised by Elias Biles. I have the pleasure to collaborate with this research, and so I would just try to go further because you don't have much time. But it's here, what matters here is that fractional operators usually use that to model phenomena that has a memory, okay? And so, it's kind of a thing. Let's go here. That's the classical definition of Riemann-Liouville fractional integral and fractional derivative. And as you can see here, since the beginning, they say, oh, it's incorporate memory in the model. But, okay, how is this memory? How you can understand this memory? And so, here is the Caput derivative. In fact, you folks here in the Caput derivative, and the reason for that is for constant functions, the derivative is 0. Okay, that's not satisfied for Riemann-Liouville case. And so, here's the main result that I would like to talk to you. And so, you can write this fractional operator in terms of statistical expectation. So, what do you have here? So, the integral, Riemann-Liouville integral, it's based, can be described in terms of the expected value of the function f. And u here is a random variable that follows beta distribution. And here, derivative of Riemann-Liouville, you can see here the expectation of the function respect the random variable w, and expected value of the f prime, the derivative. And so what you have here is a combination of expected values from the function and its derivative. And so for kaput derivative, it's also a pure expected value from the f prime, from its derivative. Okay, and why that's relevant? And so it's a statistical way to see these operators that have been used a lot, but it brings us some, some statistical interpretations. What you have. By the way, why do you know that expected value? It's an average. And so, what you can see with that? You have a lot of things, but something that you can extract from these representations, you can clearly understand the dimension of this operator. That's pretty important for a modeling point of view. And so, just for folks here in the Caputo derivative, what happens? It's here. We're going to talk about here, and let's focus on this distribution. So what happens is when 0 or alpha goes to approach to 1, it's converged to Dirac delta distribution. 1 and 1 alpha go to 0, it's the bad distribution converges to uniform distribution. Okay, it's a very interesting way and to see how they are taking the average. So it's something that interesting when you are interested to study differential equation. You always try to find the stat points. How you do that? You take where the field is equal 0, the derivative could be equal 0, but it's not true. For fractional operator, you cannot use the same approach. Because you are looking for the average of the derivatives, and to be 0, you have some positive values and negative values for the average to be 0. Now, it cannot converge for 0, for example, different of the classical case, in logistic case, for example, you converge, and the derivatives go to 0, even from positive numbers. If you have just positive numbers, you always have the average positive. You can see rapidly what happens here. Let's see this simple example. We have a parabola here. And so what happens? That's the point, the equal 0. The derivative, fractional derivative is equal 0. What I have here, the black line, is the classical case. And what happens, you're shifting the point that is 0. And that's what happens with this simple function. Okay, but what more relevant here, it's what the consequence of to see this operator, fractional operator in terms of statistical expectation. It's help us to find the dimension of the derivative. And so, why? You know that the average of some amount, some quantity, it has the same unity, it has the same dimension. And so, the dimension of these expectations is, for example, suppose that F represents population and the dimension is P. The dimension here is P over T. And you have here T raised to the power of alpha minus 1. And so the dimension is that. You can see that directly from the form, and it's something that's interesting. It's something that is interesting to realize that, because when you came from the definition, it's not so clear that it's a happen. Because you have some thing here that depend on T, and so it's not so easy to realize the dimension of this operator. And so, it's helpful for that. So let's considering these models, sure models. It's a common model in impenology. In fact, it's one of the first model in impenology. And so, what we are interested here is to see the dynamic of infected people. That's what you're looking for in general. I know that you have seen a lot of curves in COVID time. You have, let's try to control the curve. You are looking for this kind of infected people. And so you have, as my colleague said, you have the biological interpretations of these parameters. In this case, the parameter beta corresponds to transmission coefficient, and gamma it's the cover or removal rate, and 1 over gamma is every time that the person takes to recover, okay, from the disease. But what do you have here? What is important? What the people does when you try to use fractional? They just replace the derivative for the fractional derivative. If you do that, you lose the previous interpretation of the parameters. The interpretation is not the same. That's the point. If you have some message from this talk, is that, if you just change here, you are changing the meaning of the parameters. And so, because if you take the dimension of that, there's a different dimension that you have in the previous case. And so, what do you do? If you want to connect with the classical interpretation, your previous interpretations, the classical model, you have to adjust the dimension. And so, to be consistent and to better continuous has the same interpretation of contagion rates, you have to raise the power by alpha. That's the point. It's very important to keep the interpretations. You just otherwise you cannot interpretation and see what happens. And so that's important. I try to be very, very short here. And here you have two results. You try that with the China data, and what you can see here, in the alpha parameter correspond to almost 1. And for South Korea, you have 0.7. But what you have in here, you can see that alpha represents a memory effect. Now connecting with the distribution, beta distribution. What you have here, now how you can understand that this memory, for example, the memory that model is a hysteresis memory. It means that all the past, it's done. Okay, all the past is taken account, and so how it can involve, for example, mutation of virus. You can see that the memory, you can see that of memory effect in hysteresis, like in immune systems, for example. All your life matters for see how your immune system is training for a new virus, something like that. That's the idea here. And in the case of China, they have a rapid response. The huge population, they have a strong rapid response to control. And that is the dynamic is that we can understand that this parameter almost 1. Okay, I think that's all. Thank you. I will have. If you were interested in these results, you can find the details of representing fractional operator in terms of expectation. You can access this work. Thank you very much.
Thank you very much, Laércio. Oh, Esteban. If we have a very small question, we have time, but very, very quick questions, comment? Okay.
Did you look into discrete fractional calculus at all?
Oh, you think other parameters?
No, it's called discrete fractional.
Oh, no, I didn't.
I mean, it would be interesting.
Yeah, it's an open question. Yeah.
Thank you very much for the comment. So thank you very much, Stephen, for this very nice and interesting talk. Sorry for the mistake. And also I would like that we thank all the group from the Math Bio, from Unicamp, for this very nice work and all the achievements. I think it's really very nice, and really hope that to continue with this very hard work that you made during all this year, forming a lot of people, a lot of students, and bring this field to Brazil in a very strong way. So thank you very much. So now I pass the word to our chairwoman, Valeria. And we have one more talk. Wait a minute. Igor. Igor is here. Okay. Pode chamar? Now it's my pleasure to introduce Professor Igor Luiz Domini dos Santos. And the title of his talk is Discontinuous Dynamic Equation on Time Scales.
Oh, and I should say that I visited Igor's university once, long time ago in Ilha Solteira. But I don't know whether we have met there. I think we have. Because Luciano Barbanti invited me to go there. And then he also came to Rolla, and I stayed there for a couple of weeks. But you were there in my talk.
Yes. I'm happy to be here at this conference celebrating the Martin's birthday. Happy birthday. I would like to thank the organizing committee for the invitation. Okay. Here I'll talk about the generalized solutions for discontinuous dynamic equations. These equations, the discontinuous dynamic equations, extend discontinuous differential equations to time scales. Discontinuous dynamic equations admit discontinuous vector fields, offering potential for modeling hybrid systems. Frequently, real-world systems involve discontinuous jumps or abrupt changes in their dynamics. Let's say this is the motivation to study discontinuous dynamic equations. Here we analyze the existence and the relationships between generalized solutions. Theodore, Euler, Filipov, Hermes, and Krasovsky solutions. For example, Theodore solutions were studied by Tihon et al. 2012, Huberty 2010, and Santos 2015. Euler solutions were introduced to the time scales by Santos and Silva 2013. And the Hermes, Filipov, and Krasovsky solutions were introduced to the time scales framework by Santos to 2015. I will denote by capital T bounded time scales. Here A is the minimum of t, and b is the maximum of t, and a is less than b. Okay? Here we have the familiar jump operators, the forward jump operator, sigma, okay? And the back jump operator. The gradients function mi is given by sigma of t minus t. For any subset A of R, we denote A sub t, the set A intersection t. The set t kappa is given by t if the supremum of t is left dense. Otherwise, if the supremum of t is left scattered, t kappa is given by t minus supremum of t. Here is the usual and I would say well-known definition of the delta derivative of the function f from t to r. The definition, in the definition we consider t in t kappa, okay, and you have the delta derivative of f at t, denoted by f delta of t. Okay, if the time scale t is given by the closed interval from A to B, f delta of t is the classical derivative. If the time scale t is given by the integers between A and B, the delta derivative is the forward difference. Okay? Well, for a function from t to Rn, the delta differentiability is defined complement-wise. From Bohner and Peterson, 21, we have this theorem for functions from t to Rn. In Bohner and Peterson, here we have n equals 1, but the theorem also is valid for functions from t to Rn. Okay, if f is delta differentiable at t, then f is continuous at t. If f is continuous at t and t is right scattered, the delta derivative is given by a quotient. If t is right dense, the delta derivative is given by a limit. And the last one, here we have an equality involving the delta derivative. Here I will talk about delta measurable sets. Okay, we denote by script f this collection of the subintervals of the time scales t. So we have here half open intervals on the time space. So you can define the outer measuring, okay, by considering covers of a subset E. Okay? If there is no such cover of E, M star of E is infinite. Okay? So in the literature, acabado em governo, Zeno, we have the properties of the M star. So here, by using the M star, you can define delta measurable sets. Okay? So we have the condition for a set E of T, the delta measurable. We have this result. The family of the delta measurable sets is a sigma algebra on T. This family is denoted by delta. M star restricted to delta is delta measuring. It is the delta measuring, mu delta. Okay? So this notation, delta almost everywhere, is respected to mu delta. Okay? So, for example, statement P holds delta almost everywhere on T, on E subset of T. If the set N given by T in E, such that P does not hold xt as delta measuring 0. Okay, you can also consider measurable functions from T to R by considering the sigma algebra delta. So we call a function from T to R delta measurable function. Measurability with respect to sigma algebra delta. We can also consider functions f from T to Rn, okay? And the delta measurability is defined by considering its components, the components of f. Okay? Here, the debugging integral of a function f from T to R is denoted by considering delta. Okay? And this is the delta integral of f over E. A function f from T to R is delta measurable by supposing f is delta measurable. F is integrable over E if each component f sub I is integrable over E. And the delta integral of f is defined component-wise. Okay? We can define absolutely continuous functions from T to Rn, generalizing. This definition generalizes the classical continuous case, where T is given by the closed interval from A to B. Okay? This is sometimes case the definition of absolutely continuous functions, very analogy. This is an analogy to the continuous case. We have this theorem about in the based on Obada and Vivero 25, we also have the theorem for functions from T to Rn. Okay? It is an equivalence to the absolutely continuity. Okay? So f from T to Rn is absolutely continuous if the function f is delta differentiable, delta almost everywhere, and the delta derivative is integrable, delta integrable. And here we also have, let's say, the fundamental theorem of calculus, okay? This equality. Okay? So now generalized solutions. Here we have the equation 1. Okay? We have here dynamic equation. Okay? The equality delta almost everywhere. Okay? Here we have the initial condition, but here f, the vector field of this dynamic equation, is possibly it's continuous. Okay? So script C is the set of Curators solutions to equation 1. Script E is the set of Euler solutions to equation 1, and so on. A Curators solution is an arc X that satisfies equation 1 for delta almost everywhere T, and the initial condition. We have a hypothesis H here that is used for the existence of solutions. So the vector field F satisfies the hypothesis H if for each T the function of X given by F of T and X is continuous, and 2, for each X in Rn the function of T given by F of T and X is delta measurable. So in CENTOS 2015 we had this result, this existence result, okay, for the equation 1. So the vector field F satisfies the hypothesis 8. We also have here this limitation, norm of F of T and X is less than or equal to m alpha of T. Okay? T in T and the norm of X less than or equal to alpha plus norm of X 0. Okay? So there is a Curators solution for this initial value problem. This will have T in the half-loop interval from A to B1. B1 in T minus A. Okay, now Euler solutions. To talk about Euler solutions, we consider partitions of a compact subset K of R. So a partition of K is a set P given by T0 through Tn. Okay, T0 is C, C is the minimum of K, less than T1, and so on, less than Tn, and Tn is the maximum of K. Here we have a set of partitions, script P, delta of K, is a set of all partitions P, T0 through Tn, such that if Ti minus Ti minus 1 greater than delta for some I, then O of Ti equals Ti minus 1, the backward operator here, jump operator. Or we have Ti minus Ti minus 1 less than or equal delta. Okay? This is the definition of script P delta of K. We have the following lemma given by Uzenov and Karmakilon 22. For each delta, this set, okay, is non-empty. To define Euler solutions, we first define Euler polygonal arc, okay? Because Euler solutions are given by limit of Euler polygonal arcs. So we take delta greater 0 and by partition in script and we define x pi by induction. X pi is defined by x pi of Ti equals xi, x pi of T equals xi plus T minus Ti times f of Ti and xi. Here T in the closed interval from Ti to Ti plus 1. Here I 0 through n minus 1. Okay? So another solution to equation 1 is any arc x that is the uniform limit of a sequence of Euler polygonal arcs x pi j related to partitions pi j in script P delta j for some sequence delta j converging to 0. So we have the existence to Euler solutions given in Santos and Silva 2013. Okay? So by assuming growth condition, okay, for a vector field F, we have the existence to the Euler solutions. The definition for Hermes solution. An absolutely continuous function x from t to Rn is a Hermes solution to equation 1 if there exists delta measurable functions pj from t to Rn and Curators solutions xj of these initial problems such that the sequence pj converges uniformly to 0, and the sequence of the solutions xj converges uniformly to X. Okay? So the existence theorem. If you assume F delta measurable in T, and by assuming that F satisfies the linear growth condition that we have previously, okay, then there exists a Hermes solution. Krasovsky solutions. Here we have the set-evaluated function kf. It is defined by intersections of the sets. Here we have the closed complex half of f of t and x plus epsilon b. B is the unity open ball. Here we have the intersection over epsilon greater than 0. So an absolutely continuous function x from t to Rn is a Krasovsky solution if it satisfies this dynamic inclusion. X of t belongs to kf of t and x of t, delta almost everywhere in the initial condition. Based on Santos and Silva 2013, we have the existence for Krasovsky solutions. Basically, if we suppose the linear growth condition to F, we get the Krasovsky solution. Okay? Here, I note that F belongs to Kf for every t and x. So, every Kara-Teodor solution is a Krasovsky solution. We have this result given by Santos 2015. If F is locally bounded, then every Hermes solution is a Krasovsky solution. I note that the relationship script K set a subset of script H for autonomous systems in continuous time, given Hayek 1979, is not valid for the time scales T given by A, B. This is the counter-example. For this real function, the zero function, the zero solution, is a Krasovsky solution, but not a Hermes solution. Filipov solutions. We define the set-evaluated function f given by a double intersection of the sets plus the convex half of the sets f of t and x plus epsilon b minus z. Here z is z has Lebesgue measuring 0. Okay. Here we have the intersections over epsilon greater than 0, and the z such that the Lebesgue measuring of z is 0. Okay. So an arc X is a Filipov solution to equation 1 if we have this dynamic inclusion x delta of t belongs to f t and x of t, delta almost everywhere, and the initial condition. So, based on Santos and Silva, we also have the existence for Filipov solutions. Again, we suppose the linear growth condition to the vector field F, then we get the Filipov solution to equation 1. Another note, the set valued function ff is contained. This subset, this set is a subset of kf. Okay? So every Filipov solution is a Krasovsky solution. Here I note that the relationship script f, a subset of a script h for autonomous system in continuous time. See Hermes 1967 does not extend to the time scale t equals a b. To see that, we take this vector field, this real function f, this one, and the zero function is a Filipov solution but not a Hermes solution. Relationships between Curators and Filipov solutions. Okay, there's not a direct relationship between Curators and the Filipov solutions. For instance, if we consider this vector field f, a real function f, we have the zero function, a Filipov solution, but not a Curators solution. Another example for this function, or this real function, given by this equality, we have the zero function, a Curators solution, but not a Filipov solution. Okay? But I note that the function f is continuous with respect to x, so we have the equality of the sets. We have the script c equals, the script c set equals the script f, and the script f set equals the script k. Okay? Now, relationships between Euler and the other solutions. But here we consider the time scale t equals a b. Okay? In this case, we have the expression for the Euler solution. This one. This is the only Euler solution. Okay? In this case, we have the script E set, a subset of script H, and the script H set, a subset of script K. Okay? I have also this note, this relation, these equalities of the set of solutions for autonomous systems in continuous time. Our 26 does not hold for t equals a b. For example, for this real function f, even here, we have the zero function, a Krasovsky solution, but not an Euler solution. Now, in this example, for this real function, this one, we have an arc x, x such that x of a equals x0 and x of b equals 1. That is a Harry solution, but not an Euler solution. Here we also consider the relationships between Euler and Philippov solutions. For example, for this real function, f given here, the time scale t is given by a and b. So for this real function f, this one, the zeros solution is a Philippov solution, but not an Euler solution. And for this real function, this one, the zero function is an Euler solution, but not a Philippov solution. Okay, thank you for your attention.
Questions, comments?
I would have some questions. May we see the definition where you use uniform continuity? No, was it uniform continuity? Or absolutely uniform?
What definition?
The definition for continuity or uniform continuity, I'm not sure.
Absolutely.
Yeah, absolutely uniform. Absolutely.
Yeah.
So this can be obtained just from the matrix spaces, so inherited from the matrix spaces.
I think so, but I don't know. I have been working with these functions from D or their real line to Rn.
Probably you can just get it from matrix spaces and do the same I guess. Also, is it possible that can you show conditions of the function f of tx? I mean, where you give some examples for the existence of solutions. The function f of xt.
F of xt
F of tx.
for what solutions do you?
Any one of the variables. In any one of the variables. Yeah, the previous one. And the next one maybe.
Yes,
Yeah, and the next one please. Okay. I was just wondering if we let f of tx as p of t times x, I mean the linear case, does your conditions are satisfied? Just for the linear case? I just wondering.
I believe.
Because when I try to use the Euler polynomials for proving existence of solutions, I had problems. Therefore, I had to change the Euler polynomials into something else, which worked. But with this type of Euler polynomials, I was always having a problem to show that the error function tends to zero uniformly. I mean, if I would impose some conditions on the function f, in that case, it wouldn't even work for the linear case, where the most classical equation. I mean, x delta is equal to px plus q. Where there we assume that p is RB continuous and q is RB continuous. It wouldn't work for this. I was just wondering about it, but okay, thanks a lot.
One question?
suggestion about solution for second order equations or for the only for which works for the first order equations?
I have worked only on the first order equations.
An idea of this can work for higher order
I'd say I want to extend the results for the first order.
Now the talks are over, and we have Professor Martin is going to.
Yeah, I was, because everybody else is talking, so I was thinking I will say a few words also. But how do I get this off here? I mean, I didn't prepare, but I just wrote to my website. What do I do? Okay. Yeah, I don't need it now. So, the main reason why I wanted to talk is because, well, everybody is talking, and I'm talking about some people, but I never talk anything about Jacqueline because she's not giving a talk. So, about Jacqueline, I know her since she was little in Azores Island. She was a student, and then I came to Brazil in 2012 for the first time in the summer meeting. That opened a whole new area of friends for me here. And then I continued to accompany Jacqueline whenever she went somewhere. Then she finished her PhD. She went on a postdoc to Ribeirão Preto, so I went there also for a couple of weeks and gave talks there. Then she went to Brasilia as a professor, and I also gave talks there. We collaborated and so on, and finally she's here, and now I'm also here. That's good. But so she became from such little to now very, very big. She's a full professor. She's the president of gets so many prizes. So I have to say I'm very, very proud, okay, of her. Even I have nothing to do with that, but I just, everywhere where I go, I say I'm so proud. And also, I mean, many people can get 60 years old, but if nobody is doing anything for them, it will just pass, right? So now I should be very thankful to Jacqueline and also Sabrina and Tom. Is Tom awake now? Good. So, please, and because mainly at the closing ceremonies, people thank the organizers and so on, but then half of the people already left. So, and people do this again at the closing ceremony also. But now, please, let's just Jacqueline and Sabrina, and just get up, just stand up, and now everybody give a big clap. Organizing this, and also for me personally, I mean, yeah, I mean, that's the best that can happen. I have these two PhD students who took this initiative, and Jacqueline, so I'm very thankful to that. And also, I don't know, are the student workers now outside? You didn't bring them inside? Yeah, because I wanted to. Some of them are here. Okay, so maybe they could also get up that we can see them. So they have to. They're coming. And of course. Oh yeah, we will always take pictures.
Sabrina and Tom.
Yeah, in the meantime, yeah, we can, Sabrina and Tom, I don't know where should we, maybe in this direction, or I don't know. Yeah. Otherwise you always see the board. So, and now the student workers are all here, and they are doing a lot to keep everything running. And so I also wanted that they get up. They already stand up, all of them, yeah. So, and that everybody can give a big round. Okay, so now.
She wants to take a picture. You will.
Yeah, I'm going there.
We'll go there.
Yeah, this is a good picture like that. Okay, and of course, yeah, I told this to people that I never looked at the website before. I didn't really know who is coming. So this was all done by Jacqueline, Sabrina, and Tom. So I wanted to come here and then have many surprises, and it really worked. Some people told me this already by accident, or they didn't know that I'm not looking at the names, but many not, and whenever I saw them for the first time, I was really happy, surprised, and I really want to thank all of you also to come here. I mean, many different long ways, Australia, India, Turkey, Europe, America. So this is really great that you came here. Of course, not all of my collaborators and friends could come, so, and I want to acknowledge them also. Okay, now what happened? It's not secure. Okay. No, actually I don't want to go now to that. I want to go first to publications. These are, they are ordered from the latest one to the first ones. But in a life of a mathematician, are always important at the very end, so I will now go all the way down. And so acknowledge these people, advisors and first co-authors. And yeah, so that's always what stays in mind for the longest. And let's see, let's go down. Okay, so yeah, so Steve Hui was my advisor, master's advisor in San Diego. So this is my first paper actually. Okay, maybe that came out. Yeah, I know it's only because it's alphabetical. Yeah, I don't know how, but they are both in the same year, but that's my first paper. That was written 92 and 3. It came out at that time. So this is my, I have master from San Diego State University. Was my master advisor from San Diego. And then actually that paper gave me my others number 3. and later with Andre also again. But my first paper, is it 3 or I forgot the definition? One is others number is only others or?
One is you collaborate with it.
Oh, if you collaborate with others, it's number 1.
Yes.
2 is the
Okay, wait.
you're working with the collaborators.
I thought here. No, 0 is with, yeah. Yes, on that paper, yeah, 3, number 3, yeah. So that paper, that was my first paper. Okay, so then, let's see who's coming here next. I don't know, I didn't look at it before, but it's just plenty of them alone. Who is the first one here? Yeah. So that's Andre. And of course he couldn't be here. He's exactly 10 years and 2 months older than me. So that would have been 17 now. But at least we have, we have Susanna and Roman here. Okay, then also Ravi, it's my postdoc advisor. Also cannot be here because he passed away just a few months ago in December 2000. Yeah, last year, or at the end of the last year. And in fact, we're still, or we just completed a book. So this book will come out. Did Robinson ever tell you, write anything to you? Robinson, you know, from Springer? Did he say anything? Did he contact you? Because he said he might come to here because we need to sign the contract, and since I'm here, I could sign it right now. So yeah, this book we were ready to sign the contract, and almost just then Ravi had to leave. He said we'll do it when he comes back. He went to India for personal visit and also visits to universities, and just during one of these visits to the universities, he passed away. And in fact, even he was scheduled to give a talk at another university on the next day, I think. Yeah. So he didn't come back. So, but still, of course, the book will be his name. So we had to find then somebody who will sign in his legal. So his wife is doing that, and so this book will be on Sturm-Liouville theory, and it will be. It's really big book. It's 1,500 pages. But they want to split it into 2 volumes, but so because it's kind of difficult to put it together. So that book is together with Ravi and Abdullah Özbekler from Turkey. So now it's just the 2 of us. Okay, who's... Yeah, so of course here, That's is my PhD advisor, also my master advisor, because master in Germany and then the PhD in Germany. And he actually would have wanted to come, but he needs some medical treatment permanent to be. He's okay and can travel, but he should go always every week or so he couldn't come here. Okay, so these are my advisors. I have one more advisor. I'm my master advisor in San Diego, Hui, master and PhD in Ulm, Graz. And then of course the postdoc advisors. Donald Latz from San Diego State and Ravi Agarwal. Yeah, so I was in Singapore for postdoc at National University of Singapore. And then, of course, the book with Alan Peterson. So Professor Peterson, Alan Peterson, he's also well, but is old, and I guess he didn't want to come to Brazil. But yeah, we have looked together at some papers. So now I just stop here and want to go to my co-authors. Many of them are here, but just to see the ones who are not here. So yeah, with Ravi, there's 56 papers or also some books together. Then there's Tanjing. We have 26 papers together. We met online, but I went to Linyi in Shandong province, and we went in person there sometime at the beginning, and then we continued to do all this internet. But we met before, we drank many beers, but I guess he also couldn't come here. So that is Tanjing Lin from China. And then Sai Grace I never met, but he is because on some of the papers with Agawa together. So this is not my main connection, but co-author that was work done over the internet. And the same with Chengui Chang, this was Tanjing's advisor. So I also never met him. Here comes the next one, but she's here. So, and that is really a big number. I didn't know that. I mean, I wrote this program sometime and it updates it automatically, so I don't have to do too much. So yeah, 17 papers with Sabrina, so but she's here. Samir Sakar is from Egypt, so I guess he doesn't travel. I only saw him once in Veszprém. Remember, you were also in Veszprém in Hungary. And this is my other main co-author. Actually, these are my first two main co-authors, but both of them have passed away. All in like my age, I would say. So, and it was Professor Kuzinov, who was actually just mentioned in Iguer's talk. There was a series of 15 papers, and all of these 50 papers were written in the same bar in Ankara, the Yeni picnic. And I think somebody showed a picture, and he also joined two of them, also there. Bajak showed the photo before. And I think this is Shapur. This is one of my connections with Messina. It's not younger connection, let's say the last 10 years. But also 12, and that's Donald O'Regan. He has so many papers, and I even met him because I think many people now cannot meet him because he doesn't travel anymore. But back then in Athens, at the World Congress, he was there. So, and then Giuseppe is also here, and Alan Peterson was the book, and I'm not going through everybody. But Irena actually wanted to come, but then couldn't. She is in Slovakia, and Josip Gacharic is retired in Croatia. That is Jacqueline. We're at 9. So, but yeah, we have to continue because I want to come back to Brazil. Yeah, I'm not going to all of them because there's the barbecue waiting. This is my first wife, and then Risto Volov, Tandapani, Rabia Mirabeka, this is my my current wife, right? So it stops with the wives. That is Nijana, that is, she's here, yeah.
Yeah, all the same.
Ivanka is not here. But she's also from Bulgaria, but working in USA. And of course, I have to mention some of my PhD students who were not here. So Thomas Matthews is one. They are not in academia anymore. These ones who were not here, some of them, Julius Heim and Thomas Matthews. But there's also Rochana Chiochan. She is still, but in Thailand. And Suman Sanyal, my first one is in India, also in academia. And then we have one together, Rui Ferreira, together with Stephen Torres, and he's also in academia.
By the way, he sent yesterday an email to send you best compliment.
Thank you, thank you. So I'm going to stop now because the barbecue is waiting. Agnieszka is here, right? Nick wins, yes, just to see. But now we're on it. That is three, the connection that Agnieszka was talking about. And Sanket is here, yes. Roman, yes. Hugo Leiva. I'm a little bit disappointed that he's not here because every time I met him in Brazil. Yeah.
Yeah, he almost came. But
Almost came, yeah, I know. Yeah. And Bajak, yeah, they're all here. Well, not all. Eva is not here. Eva Gerajko from Poland, yeah. And Alexander Domoshnitsky from, and that's another PhD student of mine, Rashid Al-Zali. He is in academia, but in Iraq. And Patricia Wong was in Singapore when I was in my postdoc. That's another PhD student of mine, Howard Ward. And yeah, so we're now at 3. Yeah, Satyam is right now in Brno. I mean, probably if I click more, I could say something with a connection to anybody. So I stopped clicking because the barbecue is waiting. And we'll do the same thing one more time at the end of the closing. But yeah, since now many people are here, so let's just take a clap one more time and then we... Okay, barbecue.